Not so long ago, the idea that the universe operates in cycles of contraction and expansion was quite popular. It was thought that the universe initially exploded and is currently expanding, but eventually gravitational forces, meaning the forces of mutual attraction of matter, would gradually slow this expansion, bringing it to a halt, and the universe would begin to contract again. It would start slowly, like a train gaining speed, and then faster and faster back into a singularity, only to explode once more. This cycle resembles a pendulum. However, recent scientific data seems to indicate otherwise. There is no hint of the universe slowing down. On the contrary, it is expanding at an ever-increasing speed, as if something is pushing it apart, some kind of anti-gravitational force. This mysterious force has been termed dark energy. It is believed that this energy is related to the vacuum. However, a vacuum is not simply emptiness. More precisely, a vacuum is emptiness only in the first approximation, merely at first glance. If air is pumped out of a container, what remains is a vacuum. In engineering and technology, a vacuum is indeed understood as emptiness, meaning the absence of air and any other substance, but not in physics, because there is no true emptiness in nature, nor can there be. Physicists are firmly convinced of this. They know that a vacuum is merely a special form of degenerate matter, matter that exists in a zero or nearly zero state. Why nearly? Because the actual density of a vacuum is not zero, but slightly above zero by an insignificant fraction. This tiny amount, in the vast scales of the universe, creates the very effect of repelling matter. The vacuum, as degenerate but still matter, is constantly bubbling, producing and immediately annihilating pairs of particles and antiparticles, and at every point in space, they momentarily emerge from non-existence only to collapse back into the unmanifest state of matter known as the vacuum. The vacuum is an infinite ocean of virtual particles and fields. So what will happen next with this accelerating universe that is being pushed apart by the vacuum? We should admit that nothing good awaits us. The scenario for the end of the world has been dubbed the Big Rip. Our poor universe will continue to expand at an increasing speed. Galaxies will drift further and further apart, complicating intergalactic travel, which is quite unfortunate for future space tourists. 1 billion years before the Big Rip, clusters of galaxies will disintegrate. Approximately 50 million years before the end of the world, galaxies will scatter, meaning these beautiful spirals will simply cease to exist. They will also be torn apart into individual stars. 3 months before the Big Rip, all planets will drift away from their stars. Half an hour before the Big Rip, planets and stars will be ripped apart. And in 1 nanosecond, 10 to the power of -9 seconds, atoms will be torn apart, and then even elementary particles themselves. The Big Rip. And when will this sad event occur? Approximately 100 billion years from now. I hope you haven't forgotten that our universe is only about 14 billion years old. It is still young. 100 billion years is a very long time. I remind you that by then, the sun will have long since extinguished, and the death of Earth will come even sooner, when the sun dims in just 3 billion years, evaporating our oceans. However, in the latter case, humanity has a faint hope of relocating to another planet in a different star system, if that is possible. But with the Big Rip, there will be no chances. All matter will be torn apart. Damn it. Yet even in this hopeless situation, there is room for dreaming. The fact is that throughout the history of science, the human mind has studied nature as something external, separate from reason. There is reason on one side and nature on the other, which we study. However, reason is increasingly influencing nature. Even our relatively underdeveloped intellect, which has barely ventured into space on primitive kerosene rockets, is already fundamentally altering the face of the planet, shaping landscapes, and even changing the climate. What will happen in millions of years? We may begin to influence metrics on a galactic scale, and perhaps even change physical laws based on some deeper, more fundamental principles. In general, scientists who previously did not seriously consider the influence of reason on the cosmos are increasingly asserting the opposite, calling reason a universal cosmological factor that grows alongside the universe and cannot help but influence it, if only because it is a part of it. In reality, reason comprehends not the world itself, but the world in which reason exists. But while you contemplate such grand prospects, let us return to the present day. For there is one more thing we have yet to discuss, though it is unpleasant for me to speak of it. So listen carefully. Do not say later that you were not informed. Besides dark energy, which pushes space apart, there is also the concept of dark matter. We did not cover this in school because dark energy and dark matter are the latest fads in scientific fashion. They have only recently entered the vocabulary of scientists. Scientists learned about dark energy when it became clear that the universe is not only not slowing down, but is accelerating in its development. Dark matter was discovered while observing the rotation of stars in different galaxies. It turned out that the speed at which stars move around the centers of galaxies is higher than calculations would predict. This means that, in addition to the luminous mass of stars and galaxies, there is some non-luminous dark mass. Moreover, this mass reacts poorly or not at all with ordinary matter. Rather, it communicates with it only through the language of gravity, attracting it and nothing more. It is believed that these are particles of a special kind that are quite numerous, and that became centers of concentration for ordinary matter in the early stages of the universe, pulling it together into galaxies. Physicists immediately rushed to construct various theories about the mysterious particles of dark matter with which they had never encountered before, and began trying to find them with their extremely expensive installations. To this day, it remains unknown what dark matter is. However, it is known that in our universe, ordinary normal matter, from which you and I, planets, and stars are made, constitutes only 4%, just 4%, while the rest is dark matter at 26% and dark energy at 70%. Scientists of the 19th century lived in a correct mechanistic world, somewhat naive, but straightforward and beautiful. The universe, in their understanding, was eternal, infinite, predetermined, and also stationary. Atoms were indivisible particles, and space was merely the arena of action, the stage where events occurred. And time? What is time? A continuous series of changes. Physicists of the 20th century realized that it is not so simple. Their world became dynamic, unpredictable, and relative. The universe was expanding. Mass, energy, distances, and even the pace of events, time, turned out to be dependent on the speed of light. Moreover, no signals in the world could propagate faster than this speed. Physicists formally combined time with space into a single space-time continuum. Atoms ceased to be the smallest entities because their components, elementary particles, electrons, protons, and neutrons came into play. Later, other particles were discovered: neutrinos, antiprotons, positrons. Moreover, the particles themselves ceased to be absolutely solid, not in the sense that they could be broken down into even smaller components, but in the sense that they ceased, firstly, to be particles and became diffuse, acquiring wave-like properties, and secondly, when attempts were made to break them apart, they did not disintegrate into constituents, but multiplied, transforming into other particles. Roughly speaking, the more energy applied to them during collisions to break them, the more particles were formed, because energy can transform into mass and vice versa. To gain a deeper understanding of the structure of the vast universe, scientists grappled with the mysteries of the smallest details: elementary particles, fields, and vacuum. They sought to write a theory of everything, which required unifying all known interactions in physics into a single whole and understanding how it all works. Physicists were also troubled by questions: what lies behind matter? What is electric charge? What is mass? And why is everything this way and not otherwise? In their quest for answers, they devised the so-called string theory. It is now the leading candidate for a theory of everything. It turned out that, from the perspective of string theory, the foundation of matter consists of certain strings, starchy linear objects that can oscillate like strings. Calculations indicated that different oscillations of these strings are perceived in our world as different properties of elementary particles: charge, mass. The world is made of micro-vibrations. The theory turned out to be quite interesting, extremely convoluted, and very promising, yet poorly understood by many. However, what is crucial for us to grasp in this theory is that these very strings, from which everything is made, are not made of anything. When we say that something is made of something else, we mean some substance based on our everyday experience. But the situation with strings is different. Strings were invented precisely to answer the question of what substance, that is, elementary particles, are made of. And it turned out, from the perspective of this theory, that they are made of certain strings. They are primary. But what are these strings made of? They exist as pure mathematics. The fact is that verifying the validity of string theory is practically impossible. It would require such insane energy that we have not achieved in our earthly accelerators and are unlikely to ever achieve. Such energies existed only in the first seconds of the universe's existence. Essentially, humanity has come close to the moment when pure mathematics has replaced physics. More precisely, the mathematical geometry of physicists has ultimately been reduced to the geometry of space. In fact, the first person to reduce physics to geometry was Einstein. In his theory of relativity, gravity, or universal attraction is merely a consequence of the curvature of space. Massive bodies curve the space around them, and roughly speaking, they roll towards each other along these indentations, as if attracted, or, more accurately, because they are genuinely attracted in this way, as we perceive it. It has now become evident that not only gravity, but all other physical manifestations are merely consequences of the geometry of our multidimensional world. Wait, what does a multidimensional world mean? And what exactly are these strings? In the remarkable theory of strings, we cannot say what the strings are made of. The very question is meaningless, but we can describe these strings, understand what they are like. They are one-dimensional, while the space in which they oscillate is multidimensional. Not clear? Let's clarify what dimensionality means. But everyone knows this. Our space is three-dimensional. It has three dimensions: length, width, and height. You might ask, how else could it be? But in theory, it can be different. School geometry, for instance, primarily studies two-dimensional space. Two-dimensional space is a plane. On a plane, there are only two dimensions: length and width. There is no height. One-dimensional space is a line. It has only one dimension: length. And zero-dimensional space is not length. It has neither width nor height. You can imagine a two-dimensional world with flat beings living in it, and it is clear that life for them is no picnic. They have to excrete through the same opening through which they eat, meaning some flat beings excrete through their mouths. Otherwise, it would be impossible. If you try to draw a flat being in the form of a flat tube, with food entering one end, the mouth, and waste exiting the other end, you will see that your flat being has split into two unconnected parts. Humans are fortunate in this respect. In a three-dimensional world, thanks to height, a body does not split into two parts. In a one-dimensional world, the situation is even worse. The inhabitants of that world could not even pass by each other. Each resident of that world can only have two neighbors, one on the left and one on the right. A spatial dimension is a perpendicular that can be drawn to another dimension. If a perpendicular line is drawn at a 90-degree angle to a one-dimensional line, it results in two-dimensionality, that is, a plane. A perpendicular can also be inserted into the plane, adding a third coordinate, resulting in space. In a plane, only flat figures exist: triangles, circles, squares, while in space, there are volumetric pyramids, spheres, cubes, and cones. This is all easy to imagine, isn't it? However, it is impossible to imagine four-dimensional space simply because we cannot step outside our three-dimensional world and insert another perpendicular so that it is at a right angle to the other three. There is nowhere to insert it in our world. But that does not mean that four-dimensional, five-dimensional, and so on cannot exist. They can theoretically. Therefore, in string theory, one-dimensional strings, which have no thickness, oscillate in 10-dimensional space. Our world becomes 10-dimensional if we believe in string theory. Why then do we not see the other dimensions? We see only three. It is because the other dimensions are compact according to the theory. They are fixed and compacted into tiny tubular shapes whose diameters are so small that we do not notice them. Unfortunately, there are no visual representations here, so understanding it all can only be achieved through mathematics, using complex formulas understood by only a few hundred people on the planet. This raises the main question: why does mathematics, which is pure human invention, accurately describe the real world? Why does the world of mathematics, which adheres to certain mathematical rules seemingly pulled from thin air, govern nature? This is the greatest mystery of the universe. There is no explanation. Yet mathematical and geometric patterns, such as the so-called golden ratios, for example, are observed everywhere in nature. So far, no matter how deep we explore the universe and the micro-world, mathematics works everywhere, and there are no reasons to believe that it will ever fail to describe the world. Moreover, among strict scientists, there is a saying that any science is only a science to the extent that it operates with mathematics. From this perspective, history is not a science, literary studies are not a science, psychology is not a science, as they lack the precision required for science, which mathematics brings to the discipline. But why does mathematics itself work, being a bare, invented abstraction? No one knows the answer to this question. Not yet. Is it possible that physics, at the most profound levels of knowledge, has been reduced to geometry and pure mathematics? It is astonishing. But on the other hand, could it be any different? Previously, we have repeatedly mentioned that wonderful and inspiring word, evolution. Evolution is the development of matter from simple to complex, and this development has its own regularities. Why shouldn't they exist if this is a natural physical process, a direct consequence of the physical laws acting in open systems? Once, the question of whether such a complex thing as life could arise on its own from such simple earthly muck, or whether it had to be created by some sorcerer through magic, was a real stumbling block in the mid-20th century. Following the groundbreaking work of Nobel laureate Ilya Prigogine, when the physical mechanism of complexity's emergence became clear, all mysticism surrounding this question was blown away by the winds of physics, and it became evident, yes, matter can systematically complicate itself under conditions of energy influx, and therefore life can arise if there is energy input, a diverse building material, and sufficient time. Moreover, the emergence of life is a logical continuation of the evolutionary line that began at the moment of the Big Bang, continued through stellar cosmic evolution, then biological evolution, and naturally flowed into the evolution of complex organic substances. It should be noted that the first organic substances began to form not even on planets, but in space, in clouds of cosmic dust, under the influence of cosmic radiation. For instance, a complex substance such as formic acid has been found in space. As the name suggests, this substance is somehow related to ants. Indeed, in the 17th century, the English scientist John Ray isolated the molecule of formic acid from forest ants, which consists of 2 hydrogen atoms, 1 carbon atom, and 2 oxygen atoms. And this is not the only relatively complex molecular structure discovered in space. It turned out that various organic compounds are plentiful in space. There is formaldehyde, glycol, aldehydes, and more. Because of this, a hypothesis emerged suggesting that this very organic matter does not form exclusively on the surfaces of young planets, but is brought to them from space. Thus, our young Earth could have had enough organic matter brought in, or could have produced it itself. It is not a tricky matter. Under the influence of radiation from a star, a planet can create complexity and a variety of elements. One of the promising hypotheses suggests that the first life, or let's say pre-life, originated in black smokers. You know what black smokers are, right? They are underwater geysers with very hot water that erupt directly from the ocean floor. They are called black because of the color of the water jet that erupts from the bottom and the black fissures resembling smoke. These geysers were first discovered about 30 years ago. The erupting water under immense pressure contains a lot of dissolved hydrogen sulfide. Seawater contains a lot of salts from various metals. Hydrogen sulfide begins to react with seawater salt, resulting in substances known as sulfides, which are of a dense black color. Hence, they are called black smokers. In fact, these smokers and their surroundings provide the most favorable conditions for chemical reactions. First, smokers wash out a plethora of different substances from the ocean floor. Seawater also contains a sufficient amount of various substances, providing a ready building material for producing organic matter. Second, the temperatures there are high. The water in these natural reactors is overheated to temperatures of 250 degrees Celsius. And high temperature, as we already know, is the necessary energy for construction. Chemists have long known that increasing temperature dramatically speeds up the rate of reactions. Finally, thirdly, a large number of different impurities means that among them there are likely catalysts, substances that do not participate in chemical reactions themselves, but can accelerate them. Chemical experiments recreating the conditions present in black smokers have shown that amino acids, these building blocks of life, indeed form under such conditions. But what blueprints are used to assemble life from these building blocks? Who and how assembled the first living organism from them? We already know from Old Man Darwin that natural selection is needed for the emergence of life. But what selection can there be among molecules that do not care whether they survive or not, as they are non-living? How can they compete for the energy of the environment against other molecules? How can they reproduce and transmit traits? All these are valid questions, and these questions have allowed us to formulate what life is and how it differs from non-life. Here are the main characteristics of life: living objects, subjects, or beings, however you want to call them, function by exchanging energy and matter with their environment. Thus, they actively maintain their distinction from the environment. They copy themselves, reproduce, and evolve according to Darwin, meaning they pass on individual traits through inheritance. And during the copying of these traits, errors can occur. Perhaps these three factors gradually came together, and when all three characteristics of life were assembled, a complex chemical system became life. A good idea. Let's see if there is anything in non-living matter that is necessary for the creation of life. For example, if among chemical substances and reactions there is something that can be called reproduction, then we will look for something that can be termed energy exchange. Finally, we will seek something resembling natural selection in inanimate nature. Add these two previously found points, and instead of a complex series of chemical reactions occurring in the environment, we will have what can be called life. So, what do we have here? Regarding copying, there is a class of reactions in chemistry known as autocatalytic reactions. But to understand how they proceed, one must know what catalysis and a catalyst are. In chemistry, there are myriad reactions of various kinds, and among them is a group of catalytic reactions, which only proceed in the presence of a catalyst. A catalyst is a substance that does not participate in the reaction itself, meaning it does not transform into anything else, but allows other reactions to occur in its presence. The accelerator throws a catalyst into a test tube, and the reaction begins. Catalysts for various reactions are often metals. Among this group, there is a subgroup of reactions called autocatalytic reactions. In these, the catalyst is the products of the reaction themselves. This means that the more products of the reaction there are, the faster the reaction proceeds because there are more accelerators. This very much resembles reproduction. Essentially, this is reproduction. The products of the reaction in the solution, the autocatalyst molecule, which produces another identical molecule just like itself from the products of the reaction, using the reagents floating in the solution as a catalyst. It consumes the substances contained in the solution to produce similar molecules. There you have reproduction. If the reaction products are unstable, and can decay over time, then their quantity in the solution depends on the amount of food. Plenty of food means that autocatalytic reproduction increases. But if the amount of reagents from which autocatalysts are assembled begins to decrease at some point, then the products of the reaction will disappear faster than the autocatalysts can be assembled. Eventually, there will be none left in the solution. Even if the amount of food later increases, the autocatalysts will not start assembling themselves again. We remember that a catalyst is needed for a catalytic reaction, and for an autocatalytic reaction, the product of the reaction serves as the catalyst. If it is not present, the reaction will not occur, regardless of the amount of food. So what happens? The food supply decreases, and our reaction product goes extinct. If several similar autocatalytic reactions occur simultaneously in a complex solution, this can happen. For example, because the reaction produces slightly different substances. The substances may be chemically identical, but differ in spatial structure, like a left and right hand. It seems this is a hand, and this is a hand, but a left glove does not fit a right hand for some reason. The reason is that the hands differ in spatial structure. Similarly, large molecules can differ. In one molecule, a radical, a group of atoms, is attached in one way, while in another molecule, it is attached differently, with a twist. Then the altered variations of the molecule begin to reproduce themselves. There, you have random variability. What if the characteristics of different autocatalytic reactions differ slightly, for example, in speed? Then, when the amount of starting material for the reaction decreases, the faster varieties of the reaction will proceed more successfully. That is, the types of autocatalyst molecules that consume the scarce resources faster than other types will reproduce, while the others will perish from starvation. There you have selection. The autocatalytic reaction discovered by chemists is known as the Butlerov reaction, named after the Russian chemist Alexander Butlerov, who discovered it. This occurred in the mid-19th century. The excellent bearded fellow Butlerov observed how, in an aqueous solution of formaldehyde, when calcium compounds were added and simultaneously heated, a powerful chemical evolution suddenly began. Several reactions occurred, resulting in the formation of sugars. Moreover, the products of these reactions serve as catalysts for themselves. That is, the complex of reactions proceeds with acceleration. There are a vast number of sugars in the world, not all of which are sweet. Sucrose, fructose, and glucose are sweet, while cellulose or lactose are not particularly so. However, some sugars are not only unsweet, but also deadly poisonous. Now is the time to return to Butlerov, who observed something mysterious happening in a flask with a solution. Formaldehyde was transforming into a complex mixture of different sugars. This mixture gradually thickened and, as it fed on itself, solidified into stone. Why did biologists pay attention to the Butlerov reaction? Because the main carriers of biological information, that is, the information of life, are molecules of DNA and RNA, ribonucleic acid. DNA is a record of all the properties of an organism, an archive, while RNA helps read hereditary information from this archive. These two molecules are capable of accumulating and transmitting information in the form of a set of biological letters during copying. But why are they called that? Ribonucleic acid and deoxyribonucleic acid. The rib in their names comes from the word ribose. Do you feel where the wind is blowing? Notice the endings O and D. Ribose, which forms the basis of RNA and DNA, is a sugar. And how can sugars form, reproduce, and be selected in chemical reactions? We already know. Formaldehydes and mixtures with calcium compounds are abundant in nature. They have even been found in space. And there are no problems with calcium compounds. They are everywhere in the Earth's crust. Recently, it has become clear which specific natural impurities help select powerful sugars and eliminate toxic ones, aiding in the survival of those from which the foundation of our life is now built. These helper substances are called silicates, and they are also very common in nature. Furthermore, by experimenting with the Butler-Ross reaction, scientists have clarified that by adding the most ordinary apatite, a natural mineral, the Butler-Ross reaction can be shifted to accumulate almost 100% ribose. But we remember that catalytic reactions only occur in the presence of a catalyst. This includes autocatalytic reactions as well. Where did the catalyst for the reaction come from? The very first molecule of the autocatalyst. There is an answer. Primary, simple sugars, from which sugar evolution begins, can form in a formaldehyde solution under the influence of ultraviolet light. And ultraviolet light is abundantly emitted by the sun. Thus, under the conditions of Earth, life simply had no choice but to arise from the ashes of extinguished stars, from the micro-world to the mega-world. And since we are easily and straightforwardly transitioning from the micro-world of elementary particles through the macro-world of human scale to the mega-world of cosmic scale, it is important to make the following observation. We are not jumping around for no reason, but for a very compelling reason, which is that all the secrets of the mega-world, that is, all the mysteries of the cosmos, such an unimaginably vast expanse, are hidden in the unimaginably small, the micro-world, in the properties of the tiniest particles of matter, energy, and space. We have spoken much about the micro-world. Now, let us outline the universe in the broadest terms. It will pose for us a bit. As you must know, stars are not scattered evenly across the cosmic void like poppy seeds in dough. They are grouped into special clusters called galaxies. Galaxies can be spherical, but more often they are flat and spiral-shaped, resembling beautiful whirlwinds. These whirlwinds are a tangible trace in the history of the emergence of our world. Our galaxy is called the Milky Way. Why such a name? The Milky Way is named after the thick band of stars that stands out in the night sky. It looks like a trail of milk spilled across the black sky. This stellar concentration is part of the arm of our galaxy, which we view from the inside, seeing it as a personal band of stars. Thus, our entire galaxy was named the Milky Way. All the stars we see in the sky belong to our galaxy, while the stars from other galaxies cannot be seen with the naked eye. They are too far away. We can only see the galaxies themselves as faint spots. Figuratively speaking, a star system consists of a star and the planets orbiting around it. The distances between the apartments, which represent the planets, are small, but the distances between the houses are significantly larger than those between the apartments. Houses, as we know, are grouped into cities, and the distances between cities are again much greater than those within a single city. In our example, these are galaxies. The distance between them is much greater than the distance between stars in a single galaxy. Our stellar city, the Milky Way, is a classic spiral galaxy. It contains 200 billion stars, and its diameter is approximately 1 quintillion kilometers. However, Astronomers do not measure cosmic distances in kilometers. This unit is not practical for them due to its smallness. Astronomers measure distances in light years. 1 light year is the distance that light travels in 1 year. The speed of light, I remind you, is 300,000 kilometers per second. This means that if light could run in a circle, it would circle the Earth at the equator 7.5 times in 1 second. The distance from the Moon to the Earth is 384,000 kilometers, which light covers in just over 1 second. The distance from the Sun to the Earth is covered by light in 8 minutes. Therefore, we see the Sun as it was 8 minutes ago, and the Moon as it was 1 second ago. Calculate for yourself on a calculator how enormous the distance light travels in a year. Multiply 300,000 kilometers per second by the number of seconds in a year. The closest star to the solar system, Proxima Centauri, is located just 4.2 light years away. Almost at the same distance, 4.3 light years away, is Alpha Centauri. Another unit of cosmic distance is the parsec. 1 parsec is equal to 3.26 light years. Round number, 3.26. Why not 10? Because the word parsec is a contraction of 2 words, parallax and arcsecond. What is an arcsecond is clear, while parallax refers to apparent displacement. The distance at which the apparent displacement of a star in the sky due to the Earth's movement in its orbit. Most stars are so distant that they appear to us as if pinned to some celestial screen. However, a nearby star's position on the celestial screen changes due to the Earth's orbit around the Sun. The star appears to describe a tiny circle in the sky. In winter, we see it in one location, and in summer in another. It depends on how close this star is to us. If the angular size of this displacement is 1 arcsecond, then the star is located 1 parsec away from us, returning to the Milky Way. Galaxy is 30,000 parsecs, or about 100,000 light years. 100,000 years to travel from one end of the galaxy
such film has been named the Great Wall, as it is a gigantic supercluster of galaxies stretching. It is called a wall precisely because of its flat appearance. Hercules and the Great Wall of Surf. In summary, our universe, or as it is also called, the Metagalaxy, is unimaginably vast and consists of trillions of galaxies containing trillions of stars.
Our small rural galaxy, the Milky Way, is an invisible speck, a grain of dust in this dusty storm, or rather, cosmic foam. On the scales we know, the great walls, which are merely the walls of our bubble, the universe indeed appears foamy, meaning uneven, wall, void, wall, void. But on larger scales, on the order of hundreds of megaparsecs, it is quite uniform. Let me explain it this way. If we first examined soap foam through a magnifying glass and saw the rainbow-colored soap film, then a bubble of air where there is no soap, and then discarded the magnifying glass and stood on the foam at full height, looking at it from above, we would only see a white, uniform mass. This means that on larger scales, the universe is homogeneous. But if we again start to approach the cosmic foam, we will first see individual bubbles, their walls, and tanks made up of superclusters of galaxies. Then we will discern individual galaxies by bringing our curious noses close to a specific galaxy. We will see that it consists of hundreds of billions of stars. If we zoom in, we will see planets orbiting some of those stars. We are insignificant on the scale of the universe, and not only will the destruction of our planet or our solar system or even our galaxy go unnoticed, but also that of a handful measured in galaxies. Try to remove a bubble of foam from the bath. The bath will still be full. It is precisely thoughts of the insignificance of existence that come to mind when gazing at the endless black sky sprinkled with diamond-like sparks of stars. At the same time, the number of stars we can see with the naked eye, which seems vast to us, is actually quite small. With the naked eye, one can see only about 3,000 to 4,000 stars in the sky. This tiny number is nothing compared to the billions, trillions, and sextillions, yet it creates such an impressive picture. A person with binoculars can see 100 or even 200,000 stars. An eye observing the sky through a small telescope will see millions of stars. But if nothing is at hand, one must lie on one's back and throw one's hands behind one's head, staring blankly with the naked eye. Yet even the naked eye can notice that all the stars differ in brightness and even in color. One might think that the brighter the star, the larger it is, but this is incorrect, as the brightness we see depends not only on its size and luminosity, but also on its distance. A thick and powerful star may be very far away, and thus appear dim to us, while a weak little star may be relatively close, and therefore appear brighter. Astronomers classify stars according to their apparent brightness into magnitudes. A first magnitude star is very bright, a second magnitude star is dimmer, and so on. There are a total of 6 stellar magnitudes. A first magnitude star is 100 times brighter than a 6th magnitude star. Such a scale has been devised. In addition to apparent stellar magnitude, there is also what is called absolute stellar magnitude. This is purely theoretical, a product of a thought experiment. What if all stars were at the same distance of 10 parsecs from us? What would their apparent luminosity be? In other words, absolute luminosity is the brightness of a star we would see if we moved it to a distance of 10 parsecs from Earth. Then all stars would be under equal conditions, and we could say which ones truly shine brighter and which ones are dim. Some particularly sharp-eyed individuals can distinguish that different stars have different colors. Some shine slightly bluish, while others appear reddish. Is this true or just an illusion? It is true. Stars can indeed be blue, white, yellow, red, with the coldest being red and brown, and the hottest being white and blue. Our Sun, according to astronomical classification, belongs to the class of yellow dwarfs. The temperature on the surface of the Sun reaches 6,000 degrees. If the temperature were halved, our star would be a red dwarf. And if we turned the dial down to about 1,500 degrees, we would get a brown star. And if we completely extinguished its glow, we would have Jupiter, which is not a star, but a gas giant that lacked the mass to ignite as a star and emits only in the radio range. Now, let's go in the other direction and turn up the star's dial, and we will see that as the surface temperature of the star increases, its color changes from yellow through orange to white, and then to dazzling blue. At the same time, its size increases. Larger stars are typically the hottest and brightest. Astronomers classify stars by colors, by spectral classes, as they say, using Latin alphabet letters O, B, A, F, G, K, M. There is no need to memorize the letters, although it is quite easy to remember them using a mnemonic rule. An Englishman with a beard chewed dates like a carrot. This nonsensical phrase, depicting an absurd situation, quickly comes to mind and helps correctly arrange the designations of stellar classes according to the first letters of the words in this silly sentence. So, Class O represents the hottest stars, intensely shining in the invisible ultraviolet range, which is why their glow appears blue to us. The surface temperature of such stars ranges from 30 to 60,000 degrees. Examples include Lambda Orionis, Lambda Cephei, and Cassiopeia. Class B stars have temperatures ranging from 10 to 30,000 degrees. Their light is slightly bluish, or, if you will, white-blue. Examples include Epsilon Orionis, Rigel, and Gamma Persei. Class A stars range from 7.5 to 10,000 degrees. White stars are typical representatives: Vega, Sirius, and Gamma Geminorum. Class F stars have surface temperatures between 6,000 and 7,500 degrees. Their color is bright yellow. Alpha Canis Minoris, also known as Procyon, is an example of such a star. Class G stars have surface temperatures between 5,000 and 6,000 degrees with a yellow color. Our Sun belongs to this class. Class K stars have temperatures ranging from 3,500 to 5,000 degrees with a red color. Arcturus and Aldebaran are red stars. Class M stars have a rather low temperature, between 2 and 3,500 degrees, with a dark purple color. Examples include Antares and Betelgeuse. And since we mentioned the star Betelgeuse, it would be a crime not to say at least a few words about it. It is one of the most famous stars in our sky. On the sky, it does not stand out in any way, but in terms of its characteristics, it is quite unique. Generally, red stars are small, smaller than the Sun. Betelgeuse is an exception. It is simply gigantic. If Betelgeuse were to replace the Sun in our system, it would reach all the way to Jupiter's orbit, thus engulfing most of the planets in the solar system. At the same time, Betelgeuse is 100,000 times brighter than the Sun, but its mass is only 15 times greater than that of the Sun. Betelgeuse is simply a very diffuse star. The density of this hot gas sphere is much lower than that of the Sun. As you can see, the size of stars is usually related to their color. This can be most clearly observed on a diagram named after two astronomers, Hertzsprung and Russell, who over 100 years ago thought to plot all stars on one graph based on their luminosity and color. Since then, this picture has been known as the Hertzsprung-Russell diagram. On the diagram, the so-called main sequence stands out prominently, a thick band of stars in the middle of the Hertzsprung-Russell diagram. On the left of the vertical axis is the luminosity of the stars, measured in solar units. At the top are stars that shine as brightly as 100,000 or even 100,000 of our sun, while at the bottom are faint stars that shine hundreds and thousands of times dimmer than our sun. The lower horizontal axis shows the color of the stars using the letters we are already familiar with. The stars on the far left are blue and white, in the middle are yellow, and on the right are red, with the very end being brown and brownish. This is also referred to as color temperature. Temperature values are also indicated. You know that if you gradually heat metal, for example, it will first glow with a barely noticeable crimson color, then shine bright red, then bright yellow, and if you heat it to what is called white hot, it will shine white. The same goes for stars. The hotter they are, the further they move from red and closer to white, and the brighter their luminosity. As seen from the graph, stars are not scattered randomly across the diagram, but are grouped into clusters or communities, giants, dwarfs, and others. However, the vast majority of observable stars are concentrated in the main sequence, and this regularity hints at something. No, it does not just hint. It directly indicates that what we see in the picture is nothing less than stellar evolution, the life of stars. That is, the cycle of existence of stars from birth to death. Not clear? It will become clear now. If all the people on planet Earth were plotted on a similar diagram, using height instead of brightness and weight instead of color, it would result in a very similar diagram. What can we say when looking at this diagram, which is, so to speak, a snapshot of the entire population of the planet? From this temporal diagram, even though there is no time scale on either axis, we can still draw some conclusions related to time, that is, with the evolution of each individual person over time. We see on the diagram that all people are not scattered chaotically across the entire plane, filling it up, but are grouped in a certain area resembling a boomerang. Why? Because people are born small and, correspondingly, new. Then they grow to adulthood, quickly gaining weight, and then stop growing, although they continue to gain weight, but not as quickly as a growing organism becomes heavier. Therefore, the boomerang bends. In other words, the main sequence of people partly reflects life. They are born, grow, and then die. Of course, the height and weight of all people differ, but they are still confined within certain species limits. No person has ever grown taller than a giraffe, nor heavier than an elephant. Giraffes and elephants would have their own main sequence, just like stars do. An astronomer, looking at the main sequence of stars, will tell you how stars are born, live, and die. Indeed, on the Hertzsprung-Russell diagram, several types of stars are visible, but the fundamental picture does not change. The main mass of stars in the universe is neatly concentrated in the main sequence. As for how stars are born, what happens to them after death, and what this means for us, we will discuss later. And again, let's ask, what is light in its essence? Now we can pause and ponder this question. As is known, not all air vibrations can be heard by humans. There are infrasound and ultrasound, which the ear cannot detect. Could it be the same with light vibrations? Yes, the situation with light vibrations is similar. There are ultraviolet and infrared radiations that the eye cannot perceive. The sun emits these rays diligently, but we do not see them. Those vibrations with frequencies exceeding that of violet light are called ultraviolet, while those with lower frequencies than red light are called infrared. Alternatively, one could say shortwave radiation is ultraviolet and long-wave radiation is infrared. This means that the rainbow in the sky actually has more than 7 colors. We simply cannot see the other colors. Interestingly, not all earthly beings are as limited as humans. For example, bees can see ultraviolet, while snakes can detect infrared radiation. The darkening of the skin, which we call a tan, is caused by ultraviolet radiation. It is curious that infrared radiation is also perceived by our skin as heat. That is why it is often referred to as thermal radiation. Now, having familiarized ourselves with the qualitative characteristics, we only need to assign numerical values to ultraviolet and infrared light. Ultraviolet light lies on the frequency scale to the right of violet and ranges from 790 to 30,000 terahertz, while infrared values lie to the left, ranging from 1 to 400 hertz, and even further left of infrared and right of ultraviolet, there are waves. And it is interesting. What kind of waves is light? In other words, what is oscillating? Ocean waves result from the oscillation of water, while sound waves result from the oscillation of air. Yes, and to the left of infrared and to the right of ultraviolet, there are also oscillations. Why shouldn't there be? And what lies to the right of ultraviolet? With frequencies higher than ultraviolet, we find the familiar X-rays. It turns out they are just like light, only with different frequencies. The less harmful X-rays have frequencies ranging from 30,000 terahertz to 600,000 terahertz. Those X-rays with shorter wavelengths are called soft X-rays, while the high-frequency X-rays are referred to as hard X-rays. Further to the right lies the already known gamma radiation. It is not just harmful, it is deadly. Now, let's look in the other direction. What waves lie to the left of infrared? These are the familiar radio waves. They are conventionally divided into ultra-long waves, from 0 to 3 kilohertz, with wavelengths of thousands of kilometers. Long waves, ranging from 3 to 30 kilohertz, with wavelengths of kilometers. Medium waves, ranging from 300 kilohertz to 3 megahertz. These are meter waves. Short waves, ranging from 3 megahertz to 30 megahertz. These are decimeter waves. Meter waves, ranging from 30 megahertz to 300 megahertz. Decimeter waves, ranging from 300 megahertz to 3 gigahertz. Centimeter or microwave waves, ranging from 3 gigahertz to 30 gigahertz. And millimeter or microwaves, ranging from 30 gigahertz to 300 gigahertz. Practically all these waves are used by humanity in one way or another. Ultra-long waves have been used in intermittent attempts to establish long-distance communication with submarines, as long waves can penetrate water well. Long, medium, and short waves are used for regular radio communication. Meter and decimeter waves are used for television image transmission. Centimeter waves are used to heat food in microwave ovens, and millimeter waves are being explored for use in medicine for treatment. As you can see, the nature of all these oscillations, from the longest and slowest radio range with thousands of kilometers of waves to the shortest and most penetrating radiation is the same. Some of these oscillations we can perceive directly with our senses. I mean the short segment of the scale that we call visible light. And now we can only answer the question, what are these oscillations? That is, what exactly is oscillating? Light is a wave. We first learned what matter is made of. It is composed of just three particles: electrons, protons, and neutrons. Two of them are electrically charged. We have come to appreciate the periodic table of elements, where all possible atoms made from the three mentioned elementary particles are grouped. We learned from the examples of water and salt how molecules are formed from atoms. Then it turned out that, in addition to matter, there exists some invisible and intangible field in the world. It is inextricably linked to matter. The electric field is associated with electrically charged particles, while the magnetic field is generated by the movement of electrically charged particles. In fact, it is pointless to separate them, as magnetic and electric manifestations of the field are like heads and tails of a coin. There is no separate magnetic or electric field. These are two sides of a single electromagnetic field. Then we suspended a magnet on a string, and then a charge and quality, causing them to move, oscillate, and propagate waves through their field. You guessed it, those very waves that span the frequency range from 0 to infinity. Radio waves, light, ultraviolet, X-rays, gamma rays. These are simply electromagnetic waves, meaning oscillations of the electromagnetic field. It permeates the entire universe. It is just that in some places, the field is denser, while in others, it thins out to 0. Relativity. Einstein's theory of relativity is the most well-known physical theory to the general public, although it is neither the strangest nor the most complex. Quantum mechanics is both more complex and stranger. However, almost everyone, from young to old, has some understanding of the theory of relativity. Now you will have this understanding as well, regardless of whether you are young or old in a good way. Writing a separate book with diagrams and graphs about this theory would be necessary, but for now, we will have to limit ourselves to just a few conclusions from the theory of relativity. They are quite non-trivial. Einstein showed that as one approaches the speed of light, the mass of an object increases. We already know this. The linear dimensions of the object shrink, it becomes shorter, and time slows down for it. What does this last fact mean? It means that all processes for this object occur more slowly when viewed from the outside, of course. Thus, if 1 minute passes on a spaceship traveling at near light speed, years or even centuries may pass on Earth. But that's not all the oddities. Einstein interprets gravity as the curvature of space and the slowing of time. In other words, what we perceive as gravity, the tendency of objects to be attracted to the Earth, is merely a side effect of curved space. The most vivid way to visualize this is with an image that one can imagine to understand it. Imagine a perfectly taut and gridded rubber surface. This is space without gravitating masses. All lines and angles here are straight, and we have a model of a two-dimensional surface, that is, a plane. On the plane, there is only width and length, but no height. A weightless little ball, a photon, will roll along this straight flat space in a straight line. This straight space is called Euclidean, in honor of the Greek geometer Euclid. If we now place a massive sphere in the form of a heavy planet on this plane, the rubber surface will bend, and the lines and angles drawn on the surface will stretch and curve, with the curvature increasing the closer one gets to the sphere. If we then launch a small test ball along this rubber surface, its straight trajectory of movement near the heavy sphere will bend along the curved surface of the rubber. If the speed of the ball is low, it may even roll into the dip created by the heavy sphere, as if being attracted to it. But this attraction is merely a consequence of the curvature of our two-dimensional space. The same happens with our three-dimensional space. It is just not as easy to visualize its curvature as it is to visualize the bending of a two-dimensional surface, that is, a plane. Thus, every mass in our world, from the lightest particles to the heaviest stars and galaxies, creates a curvature of space around it, which ceases to be straight Euclidean. But that's not all the tricks of old Einstein. According to his theory, mass not only curves the space around it, but also slows down time near it. And the greater the mass, the more pronounced this effect. Consequently, time flows slightly slower near the Sun than it does near the Earth. Despite all these completely non-obvious things, Einstein's theory has passed all possible experimental tests, and the effects of space curvature and time dilation have been instrumentally confirmed. The theory has been brilliantly validated, of course, for the masses we usually deal with and live on. The effect of space curvature and time dilation is weak on Earth, but with sufficient effort, it can be detected. And the physicists have indeed strived for this, I assure you. Therefore, today, the theory of relativity is one of the main and most beautiful treasures in the treasury of physical science. Periodically, excited physicists take this theory in their trembling hands, and without tearing their eyes away, quietly sigh, admiring it, unable to contain their admiration. How have physicists turned away from reality? Physics differs from mathematics in that it describes not bare numerical abstractions, but the concrete world. Although behind mathematical formulas, there is always some reality, and if the formulas incorrectly describe that reality, then the theory is wrong. One must find other formulas, constructing a visual model in one's mind of how physical processes occur. Water flows. A body moves under the influence of gravity. An object heats up. A ray refracts. If the found formula corresponds to the results of experiments, it means that the visual model that arose in the theorist's mind corresponds to reality, at least up to certain limits. However, this was the case only until the beginning of the 20th century, as earlier physics primarily studied the macro world and then shifted to the study of the micro world. And in the physics of the micro world, clarity began to fade. It is easy to imagine a particle as a small ball, easy to imagine a wave, but how does one visualize a wave particle? How does one envision that one electron passes through two slits simultaneously? How does one conceive of a virtual quantum or an excited vacuum? There are no such objects in our macro world. This is the problem of modern physics. Humans are animals adapted to life in a world of solid bodies, that is, in the macro world. What we become accustomed to from childhood, living in this world of solid bodies, we consider clear, that is, understandable. Clarity is merely a function of habit, nothing more. The penetration of the mind into the micro world has deprived physicists of clear images, leaving only abstract thinking and pure mathematics in their toolkit. We have no and cannot have representations of the micro world. Our bodies are geared for survival in the macro world, but it was so painful to part with the familiar and natural. For instance, it is completely natural for us that parallel lines do not intersect. However, this is natural for us only because we are accustomed to living in the so-called Euclidean space, where the familiar school geometry applies. Yet physicists are already operating with other geometries of curved spaces where parallel lines can indeed intersect. Physics studies the world and therefore cannot do without clarity, believed the old-school physicists, for behind formulas always lies some reality. We simply need to devise models that adequately describe reality and allow us to understand it not only at the level of formulas, but also visually. We can describe the compression of springs or the flight of a bullet with formulas and can vividly imagine these processes. So let us find visual models that provide a clear representation of events in the microworld. But this is impossible, the new generation of physicists firmly objected. How can one imagine a state vector or a wave function? You will now have to rely solely on formulas, you old goats. And how despicable you all are, the old-timers complained. For it cannot be that nature does not know something. Most likely, it is we who have yet to learn something about it, to uncover some secrets. Therefore, it seems to us that randomness and uncertainty reign in the nature of the microworld, and that a flying electron is simultaneously present in all points of space. In reality, we simply need to continue studying the world and finally grasp the reality that is still hidden from us. For what emerges from the formulas contradicts intuition. No hidden reality exists, kids. The youth cynically laughed at the old physicists, calling the old-timers' desire for clarity naive realism. And as for intuition, it is merely a product of the macro world and our senses tied to the macro world. Forget about it. And you already know that among the disgruntled old-timers were such giants, such pillars of physics as Planck, Bohr, and Einstein, who themselves stood at the origins of the worldview catastrophe. These individuals were bewildered and tried to find at least some visual models to describe the wave-particle duality and other wonders of the micro-world. Meanwhile, the new generation merely waved their hands, not even attempting to find any images, content to rely solely on formulas. Regarding this dramatic dispute, one of the new wave physicists, Max Born, remarked, "Our debate cannot be called a purely scientific discussion. Rather, it resembles religious disputes of the Reformation." Thus, there was little hope for reconciliation, and he was generally right. The worldview catastrophe was such that some physicists even became fascinated with ancient Indian philosophy, as did Erwin Schrödinger, for example. The catastrophe was exacerbated by the fact that physicists had to abandon not only the concept of physical reality, but also the concept of objectivity. It was once believed that there is an objective world and a subject, the person studying that world. The objectivity of the world lies in the fact that it does not depend on the subject. It simply exists regardless of whether we study it or not, and who does so, Ivanov, Petrov, or Sidorchuk. The laws of nature do not depend on us. We merely discover them. However, the laws of the microworld turned out to be so strange that the observation of the subject significantly influenced reality. Objective reality proved to be dependent on the subject. Here is an example. The double-slit experiment with an electron that passes through two slits creates an interference pattern on the screen. So, one electron passed through two slits. How astonishing. Or perhaps it passed through just one. The classical physicist asked hopefully, what can be verified? A detector needs to be placed near one of the slits to record whether the electron passed through that slit or not. If the detector registers the electron, then it indeed passed through that slit. If it does not, then it went through the other one. And what do you think happened? As soon as the detector is set up, as soon as observation begins, the electron starts passing through only one slit, either this one or the adjacent one. But at the same time, the interference pattern on the screen disappears. Interference vanishes when the electron knows we are observing it. That is the problem. The electron begins to behave like an ordinary particle, and when we do not observe it, when we turn off the detection device, it behaves like a wave again, and the wave interference pattern reappears on the screen. How unexpected! One of the main physical formulas of the micro world, which describes the so-called state vector, describes not only the state of the studied quantum system, but also our knowledge of it. Our knowledge is included in the formula. But could the old-school physicists easily come to terms with this? And when theoretical physicists began studying the vacuum and the smallest structures of being, the last remnants of clarity in the form of mental images and collages dissolved, leaving only pure formulas. What can be done? The world is governed by mathematics. Where does time come from? Anyone who has heard of the theory of relativity has surely been impressed by the tricks with time. How is it that time slows down as speed increases? What does that mean? It means that all processes, including the slowing of time, occur more slowly. But wait, a smart person in round glasses might say, if all processes are slowing down, including clocks, then how do we know that time has slowed down? We simply wouldn't notice it, as all processes have slowed down, right? Inside such a system, where time has slowed down, no one will notice anything. It will only be noticeable from the outside, as everything is understood in comparison. The sizes of objects are measured by comparing them to a ruler, and time intervals are measured by comparing them to intervals counted by clocks. But if there is nothing to compare with, how can you know? Therefore, the slowing of time in a certain system can only be judged by an external observer who is outside that system. That observer can say, "Oh, the clocks are ticking slower, and you are aging more slowly than I am, and you are moving and thinking. You must be slow." In general, the theory of relativity showed that not only mass and space are relative, but also time. The mass of a body increases with speed. Linear dimensions of a body, that is, space itself, contract, and time slows down. But what is time? Many philosophers have pondered the nature of time. Physicists of the Newtonian era believed there is matter, from which everything is made. There is space as the container of all things, and there is time as the measure of the duration of ongoing processes. Matter is the actors, the stage is space, and the duration of the performance is time. Moreover, space and time will remain even if matter is removed from the world. Modern physics holds a different view. There is only quantum existence, which manifests itself in three forms, as matter, space, and time. There is an infinite ocean of vacuum in which everything occurs, and its agitation is perceived as substance and field. At a practical level, substance is clear. We ourselves are substance and deal with it throughout our lives. Space is also not confusing. If it's far away, it's better to fly by plane. It moves faster through that very space. And in general, if you are not in space, then where would substance be located? Here, we have a misunderstanding. No, it's all very simple. But what about time? What is it? How can you touch it? Can it be isolated as a separate entity? Why do people talk about the arrow of time, about it passing irretrievably, that the past cannot be returned? I will answer these questions immediately. There is no time separate from matter. There are only processes that occur. We speak of time only when events happen. No events, no time. When a positron collides with an electron, turning into quanta of electromagnetic radiation, that is an event. A sparrow chirping, that is an event. A person dying, that is an event. Since something is always happening in the world, we speak of the presence of time. Time, like mass and distance, is measured by calibrated segments. We have agreed that this segment of space is considered a meter. This piece of mass is a kilogram, and this segment of time is a second. The standards of the meter and kilogram are stored in the Paris Chamber of Weights and Measures. The meter standard is made of a solid, nearly temperature-invariant platinum-iridium alloy. The kilogram standard is made of the same material and is a cylinder with a height and diameter of 39 millimeters. However, you cannot place a second in the Chamber of Weights and Measures. Its standard is embodied in highly accurate atomic clocks, a devilishly complex device that uses unchanging natural processes, electromagnetic oscillations of an excited cesium atom. For example, in everyday life, we use simpler devices to measure time, ordinary mechanical or electronic clocks, which due to their primitiveness constantly need to be adjusted to precise time signals. Some electronic wristwatches can already receive precise time signals transmitted via radio and adjust themselves. We look at the circular motion of the hands and determine the time that way. In the past, people measured time by the flow of sand in hourglasses or water in water clocks, or by the movement of shadows in sundials. In general, people have always measured time by some uniform motion because time as a separate substance does not exist. There is only the movement of material objects in space, which we perceive as time. But if time does not exist, why then does time have properties? The same smart person in round glasses might ask. Such properties, for example, as unidirectionality. In space, one can move in all directions, but in time, only into the future. A valid observation. But what do we understand by the unidirectionality of time? What does it mean that one cannot move into the past? It means that one cannot become younger. For example, we all proceed in our own way, from childhood through youth and maturity to old age, and we cannot stop this process. If a glass breaks, we cannot go back in time and move it further from the edge of the table. If we run out of money or other resources, we cannot return to the past when we still had them and replan our expenses. Why can we travel in space, but not in time? Precisely because space exists, while time does not. One cannot travel in anything. We see objects moving in space. That is the entire illusion of time. Want to go to the past? Just move all objects, all fields, all particles in the world to the positions they occupied in the past and give them all the speeds they had then. That's all. Can this be done? No, because the glass has already broken, and we have aged and cannot reverse these processes. Herein lies the entire trick. Time is irreversible. Some physical processes are irreversible. This is the apparent phenomenon of the irreversibility of time. We simply cannot reverse certain forms of the movement of matter. We cannot rejuvenate ourselves. We cannot return the energy spent from the battery of a flashlight because it has already transformed into light and heat, and the photons of radiation have irretrievably spread throughout space. How can we now collect them by the quantum in the universe and shove them back into the battery? Not at all. Therefore, time, or rather, most processes of movement, are irreversible. Moreover, from the perspective of physics, they are irreversibly so in principle. This leads to many consequences, such as the impossibility of creating a perpetual motion machine of the second kind, that is, a machine that would convert waste heat into useful work. This idea of creating a perpetually spinning wheel has occupied humanity for hundreds of years. Even in ancient times, no, this time, not the Greeks, the Indians dreamed of building such a device that would spin on its own forever. However, the peak of invention occurred during the European Middle Ages and the Renaissance. At that time, mills were being built everywhere. European mechanics pondered, could such a device be constructed that would not require any external drive, neither the flow of a river nor the wind? After all, not everywhere are there streams and rivers. Not everywhere does a constant wind blow. How wonderful it would be to build and start such a wheel once, attach millstones to it for grinding flour, and let it spin on its own. Perpetuum mobile, eternal motion in Latin. They were naive people. We are the smart ones today. We understand that there is no free lunch in the world. Everything has a cost. Physicists call this everyday principle the law of conservation of mass and energy. Hundreds of years ago, thousands of inventors seriously tried to patent the creation of a perpetual motion machine. The proliferation of these ridiculous projects so exhausted the scientific community that the Paris Academy of Sciences decided in the late 18th century to no longer consider perpetual motion projects because a perpetual motion machine is impossible. Its existence contradicts the law of conservation of energy, and that's that. But this did not stop the inventors. Over time, they devised increasingly complex designs, and with the advent of steam engines, they began to design perpetual motion machines of the second kind. What does this mean? I will explain. Perpetual motion machines of the first kind are mechanical devices that, according to the inventor's design, are supposed to work forever. Perpetual motion machines of the second kind are thermal machines that can convert the surrounding heat into useful work. This requires some clarification, but first, let's ponder a bit about perpetual motion machines. Suppose that a perpetual motion machine is possible. We have devised such a wheel reconstruction that can spin forever. After all, nature knows examples of perpetual motion. The Earth spins around its axis and around the Sun for billions of years and doesn't even think of stopping. What could be a better perpetual motion machine? Moreover, the laws of mechanics state that any body, if no forces act upon it, will either remain at rest or move uniformly and in a straight line. And not always in a straight line, as we see in the example of the Earth orbiting the Sun. So why do scientists confuse us by claiming that perpetual motion is impossible? Perpetual motion is certainly possible. Moreover, the movement of the universe cannot be eliminated. But nature is inherent to matter, which only exists in motion. And the simplest perpetual motion machine is an ordinary wheel on an axle. If you spin it well, that is, impart energy to it, theoretically, the wheel will spin forever, just like our planet, because the law of conservation of energy exists. And since we have applied energy to the body, it cannot disappear without a trace. The wheel must spin forever. But we know from experience that it will not spin forever and will soon come to a stop. This means that some forces are indeed acting on the wheel, and the energy we stored is leaking away like water from a leaky bucket. What kind of parasitic forces act on our wheel? Just ordinary friction forces, that is, forces resisting motion. The wheel rubs against itself gradually, heating up. Rub your palms together vigorously. They will warm up and turn red. Here is a typical example of the action of friction. Your mechanical energy is converted into useless heat. Moreover, the wheel rubs against the air, heating it and creating wind. That's why airplanes and cars try to be more aerodynamic, so that they don't have to waste extra fuel on air resistance. And the moving parts of the wheel and gears burn energy on special bearings, lubricating them to reduce energy losses due to friction. Well, if our hypothetical spun wheel rotated without any axle in space, where there is no air, then it would rotate forever, just like the planets do. Okay, let's assume we managed to create an ideal frictionless bearing, place the wheel in a vacuum chamber, and somehow spin it there. Then we would have a perpetual motion machine, but a very foolish one, because we don't need perpetual motion for its own sake. We need useful work. What will we do with this perpetual motion machine? Stare at it, blinking. As soon as we attach any axle with a millstone to this perpetual wheel and make it grind grain, that is, actively slow down our wheel with work, it will immediately come to a stop, and we will have to spin it again, overcoming resistance. Isn't it simpler to just grind the millstone by hand? Why bother with an intermediate wheel? A working mechanism cannot extract energy from nowhere. Life has arranged itself such that if useful work is needed, energy must be sourced from somewhere. Either we eat well and do the work ourselves, or let the wind turn the mill, or let the river turn the turbine of the power station. There is also a lot of hidden energy in fuel. If it is burned, a lot of heat is produced. This heat can be used to heat water in a boiler, turning it into steam, and the pressurized steam can push a piston or turn some device. This is precisely what happens at thermal power plants, where superheated steam spins the rotor of the electric generator. But then, when the fuel burns out, all the heat it produced will go up the chimney, dissipating into space, and the heat from friction will also dissipate into space. In general, any work that we perform ultimately boils down to one thing: irretrievable losses of energy in the form of dispersed heat. That is the nature of things. All highly organized forms of energy, mechanical, electrical, kinetic, ultimately transform into low-organized waste heat. But can we collect it back from the surrounding environment? Then we would have a perpetual motion machine of the second kind. We would not violate the law of conservation of energy, as we would not be taking energy from nothing. We would simply gather the energy that is already dissipated and make it work again. Inventors pondered this and began to design various fantastic projects, the essence of which ultimately boiled down to collecting dispersed heat from the environment to concentrate it, heating something specific for subsequent useful work. However, strict physicists pointed out to these would-be inventors each time, "Guys, it is fundamentally impossible to transfer heat from a colder body to a hotter one, making it even hotter. Heat can only flow from hot to cold, not the other way around. Why is this so? We will soon understand. But for now, let's listen further to physics. To perform any work, a difference in potentials, a difference in energies, is needed. This can be a difference in electrical potentials in electrical engineering, or a difference in potential energy of bodies at different heights. For example, a weight lifted above the floor level in a cuckoo clock has more energy than the same weight on the floor. Or flowing water from a height has energy due to the difference in heights. It can turn a turbine or a water wheel. If there is no difference in height, and accordingly no flow, the wheel will not turn. The same goes for thermal machines. All useful energy is derived from the temperature difference between a hot body, such as burning fuel, and the cold surrounding environment. If there is no potential difference, pressure, electrical, temperature, or height, there will be complete stillness. There will be no movement capable of doing useful work. A flow of energy is needed. An electron sees the eye of flowing water transferring from a hot body to a cold one. No heat, no flow, no work. The transfer of heat from a cold body to a hot one is also incredibly unlikely, like water flowing uphill by itself. Therefore, a perpetual motion machine of the second kind is impossible. There is plenty of parasitic heat around us, in the air and in water. But try to gather it. Try to organize a bunch of heat from which you can then create a reverse flow into the surrounding environment for the sake of utility. Imagine a large gas cylinder divided in half by a partition. In the left half of the cylinder, we have gas under high pressure, and in the right, under low pressure. The temperature of the gas is the same. This means that the speeds of the molecules in both parts are identical. It's just that on the left, where the pressure is high, there are more molecules, and their travel distance between collisions is shorter. There is a potential difference. On one side, high pressure, on the other, low pressure. What will happen now if we remove the barrier between the halves of the cylinder or open a valve on it? The pressure will equalize, and the same number of molecules will be swirling in both parts of the cylinder. While the pressure is equalizing, we can place a turbine underneath to generate rotation, a useful job. But once the pressure equalizes, the turbine will stop spinning. Can it happen that billions and trillions of gas molecules in the cylinder suddenly and randomly gather in one part of the cylinder? No, of course not. Statistically, this is practically impossible. They move chaotically in all different directions. Now let's imagine another situation. The same cylinder, but now the gas in the left part is heated, while in the right, it is cold. We remove the partition. What happens? The energetic and fast hot molecules from the left side begin to collide with the cold, that is, slow molecules from the right side, nudging and pushing them. In this process, they will lose some of their speed, and as a result, after some time, the speeds of the molecules will average out, meaning the temperature will equalize. Could it now happen that billions and trillions of gas molecules suddenly and randomly separate into two groups, very fast and very slow? No, of course not. This is practically impossible. They are moving chaotically and in all different directions. This is where the phenomenon of the unidirectionality of time lies. It has a purely statistical nature. Simply put, most processes occurring in the world are statistically irreversible. Time as such does not exist. There are only irreversible processes from the perspective of probability theory. No, they are not impossible. They are just so unlikely that the time needed for their realization exceeds the lifespan of the entire universe. This means that everything in our world leads to averaging and degradation. Someday, all energy reserves in the universe will be spent and transformed into dispersed heat. All irregularities, potential differences, will average out, and nothing will happen in the world. This sad picture is referred to in science as the heat death of the universe. But we have an air conditioner at home, a particularly clever listener might say, and it easily transfers heat from a cold body to a hot one. It prevents temperatures from equalizing outside and inside, creating coolness in the apartment while it's hot outside. The air conditioner takes the heat from the apartment and dumps it outside into the heat. It also works against averaging, artificially creating a temperature difference in the room. However, to create this temperature difference, we still consume energy from the grid. Of course, we can locally hinder nature in its drive toward connection and heat death. But to do this, energy must be expended, meaning it must be sourced from somewhere, applied to the necessary place, and visible work is done in that place to counteract the blind and dead forces of nature, in opposition to nature. The trap, when stars explode, this story happened about 450 years ago, on a beautiful November evening, when a young Danish man named Tycho Brahe stepped outside and, as usual, looked at the sky. Tycho Brahe was an astronomer, astrologer, and tireless duelist. In one duel, Tycho had his nose chopped off by a sword, not to shock those around him with his disfigured face. Brahe wore a silver prosthetic nose for the rest of his life. So, stepping outside on that beautiful November evening in 1572 and raising his silver nose to the sky, Tycho Brahe froze in astonishment. He, who by that time knew the pattern of the night sky by heart, all the main stars and constellations, suddenly saw a new star in the constellation Cassiopeia, which had not been there the night before. Is that possible? Since ancient times, it has been well known. Stars are eternal and unchanging. The same stars grouped into the same unchanging constellations shine down on people at night for centuries and millennia. Since the beginning of time, there has never been a case where a new star suddenly ignited in the sky, and not just some barely noticeable star that you can't see without a telescope, but a star of considerable brightness, visible to the naked eye. It suddenly shone in the sky, altering the familiar pattern of the constellation. Since then, the suddenly bright star that appeared in the sky has been called a nova or supernova. It flares up suddenly, unexpectedly for everyone, and shines for a short time before quietly fading away. What distinguishes novas from supernovas? First of all, it is important to understand that the flare of a nova or supernova is not the sudden birth of a star, followed by a lightning-fast demise. It is merely an explosion of an already existing star. This star is so dim in the night sky that it is practically unnoticed. But during the explosion, such an astonishing amount of energy is released that the barely discernible star in the telescope instantly becomes a first magnitude star, creating the complete impression that a new star has ignited in the sky. Hence the name, nova or supernova. A nova differs from a supernova only in the power of the explosion. It's somewhat like an atomic bomb versus a hydrogen bomb. The atomic bomb is terrifying, while the hydrogen bomb is life itself. A nova increases its brightness during the explosion by thousands and hundreds of thousands of times, while a supernova increases it by millions and billions of times. Imagine a binary star system consisting of two stars orbiting each other. Astronomers say that in such cases, the stars orbit around a common center of mass, held together by mutual gravitational attraction. But one of these stars is a dense white dwarf, while the other is a large but loose, fairly low-density star. the sturdy white dwarf constantly siphons gas from its partner, gradually stealing gas from the upper layers of the inattentive giant. As a result, a layer of hydrogen forms on the surface of the dense white dwarf, which, gradually accumulating and heating up under the strong gravitational field of the white dwarf, explodes, similar to how hydrogen explodes in a thermonuclear bomb. This is not the even combustion we observe in the center of ordinary stars, but rather an explosive, irregular process of sharply burning off the accumulated foreign hydrogen on the surface of the white dwarf. Moreover, these flares, which sharply increase the luminosity of the binary system by tens, hundreds, or thousands of times, can occur not just once or twice, but periodically, as each new portion of fuel accumulates on the surface of the white dwarf. This is what is called a nova, although in reality it happens in a binary star system as a result of the interaction of two stars, one of which is a dense white dwarf, and the other a loose giant. Such a flare can last for several days and continue for years until all the hydrogen stolen by the white dwarf burns off, and then there will be another cycle. A supernova explosion is an entirely different matter. Such a catastrophic event occurs with very massive stars, which are many times heavier than our Sun. These giants gradually build up heavier and heavier elements from the periodic table layer by layer, as is expected of proper stars. In the outer layers, hydrogen is still burning. One layer below is helium, followed by silicon, magnesium, carbon, and so on, all the way down to iron, which is synthesized at the very center under immense temperatures. The star can no longer use its fuel for further synthesis. We now understand why iron is the most stable element with the highest mass defect. To break down iron, or, conversely, to add particles to it, one must apply external energy, whereas for elements lighter than iron, the situation is reversed. They burn themselves, providing energy for the star's luminosity. The enormous mass of the star is necessary, in this case, for the gravitational forces to compress the matter sufficiently to reach the temperatures required for iron production. Thus, in the center of a massive star, an unburnable residue in the form of iron settles, and the thermonuclear burning, which had been pushing against gravity with tremendous radiation, ceases. The force of gravity, now unopposed, begins to further compress the matter at the center. However, since the star is gigantic, its gravitational forces are so great that they start compressing electrons into protons, forming neutrons. Instead of nuclei, which had electrons swirling around them, only neutrons remain. As we have discussed, the density of matter suddenly increases, meaning the center of the star collapses inward sharply, followed by the outer layers, which had been burning slowly and uniformly. As a result of this catastrophe, quadrillions of tons of fuel rush downward, or rather, toward the neutron center of the star, heating up and raising the temperature to the point where the orderly thermonuclear burning transforms into an uncontrollable thermonuclear explosion, which literally blows the star apart in all directions, leaving behind a tiny neutron core, while all the quadrillions of tons of matter are scattered into space. It is at the moment of this monstrous explosion that the additional energy is generated, allowing large nuclei to overcome electrical repulsion and bind together with short-range nuclear forces, forming nuclei heavier than iron. Then, as the atomic nuclei are scattered around, along with the unbound free electrons, the electrons become less energetic and are gradually attracted to the nuclei as they cool down. This results in normal matter, quadrillions of tons of atomic cosmic dust made up of a mixture of various elements from the periodic table. This matter serves as the foundation of life. Clouds of this material slowly gather together under the influence of gravitational attraction, first forming a dust nebula in the shape of a rotating dust disk, at the center of which a new star ignites from the remnants of hydrogen, while planets gradually form from heavier elements around it. Why are planets predominantly made of heavier elements? Because, once ignited at the center of this dust cloud, the newborn star begins to sort the surrounding periodic dust with its radiation, pushing lighter elements outward, while heavier ones remain closer to the star. As a result, we have what we observe in our solar system, where large gas giants like Jupiter orbit farther from the Sun, while smaller, denser planets such as Mercury, Venus, Earth, and Mars revolve closer to the Sun. Essentially, they are metallic spheres covered with a crust of oxides, or, simply put, rust. We live on one of these rusty metallic spheres, and we like it. But let's return to supernovae. I would like to guide the listener a bit more around this greatest stellar catastrophe so they can fully grasp the power of this natural phenomenon. The explosion of a supernova is so monstrous that in just a few seconds and minutes, it releases more energy than all the stars in the entire galaxy combined during the same time. And there are, I remind you, 200 billion stars in our galaxy. What a concentration. After the explosion, which lasts about a month, an instant compared to the hundreds of millions of years of a star's life, what remains of the former giant, which once spanned millions of kilometers, is a tiny neutron star with a diameter of about 15 kilometers, surrounded by an expanding nebula. However, even supernovae are not the limit of stellar madness. There exists a phenomenon known as hypernovae, exploding stars whose power exceeds even that of supernova explosions. This is how stars with more than 80 times the mass of the Sun explode. It is believed that hypernovae are responsible for the most dangerous cosmic phenomenon, so-called gamma-ray bursts. Gamma radiation is a form of hard radiation, a primary factor in the devastation caused by nuclear weapons. It is gamma rays that cause the terrible radiation sickness from which people suffer and die in agony. Occasionally, radio astronomers detect incredibly powerful bursts of gamma radiation in the sky, lasting from a few hundredths of a second to several days, though usually only seconds. During these seconds, the amount of energy released in the form of gamma rays is equivalent to what a dozen stars like our Sun would emit over 10 billion years. One could also say that a single hypernova explosion emits as much energy in seconds as all the stars in the universe do during the same time. Can you imagine the horror? Fortunately, all detected hypernova bursts have occurred outside our galaxy, because if such an explosion were to happen anywhere within our galaxy, say, within 300 parsecs, roughly 1,000 light-years, life on Earth would be completely or partially annihilated. It is possible that our planet has already experienced a similar catastrophe in its history. There is a hypothesis that around 450 million years ago, a powerful downpour of gamma radiation struck Earth, leading to the extinction of 60% of all species on the planet. This catastrophe is known in science as the Ordovician extinction. Its causes remain unknown, but a hypernova could very well be the culprit. Thank goodness such horrors happen very rarely. But what does rare mean? Do you often get hit by a car? I hope never. For any individual person, this event is highly unlikely. But there are billions of people, and therefore every day, 3,500 people die under the wheels of cars worldwide, accumulating to over 1.25 million in a year. And that's just the fatalities, not counting the injured. Similarly, astronomers observe gamma-ray bursts almost every day in all corners of the universe. Interestingly, hypernovae explode much less frequently than supernovae, yet they are detected more often. Approximately 50 supernovae are recorded each year, while there are hundreds of hypernovae. Why this contradiction? Because hypernovae are so powerful that their radiation reaches Earth from anywhere in the universe after the explosion. For example, scientists detected one on March 29, 2003. A fairly powerful hypernova exploded 800 megaparsecs away from us. Note that it is not parsecs, but megaparsecs, meaning millions of parsecs. Ordinary supernovae that explode very far away can go unnoticed. They are not detected as frequently as hypernovae, simply because hypernovae are more noticeable due to the sheer scale of the phenomenon. However, since there are countless galaxies in the universe, we can say that in one galaxy, a hypernova occurs on average once every 10 million years, while several ordinary supernovae explode every 100 years. This means that practically every day in the universe, someone is getting hit by a car. A civilization, or just life, could be perishing on some planet. To better understand the incomprehensible power of hypernovae, one can provide this example. One of the powerful gamma-ray bursts recorded by astronomers was visible from Earth with the naked eye because, along with gamma quanta, the star emitted intensely in the normal optical range, that is, invisible light. Although the explosion occurred very far away, 7.5 billion light-years from the solar system, if it had happened in a neighboring galaxy, like the Andromeda Nebula, the night sky would have shone with a brightness equal to that of a full moon. And if the explosion had occurred at the far edge of the Milky Way, its visible brightness would have equaled that of the sun during the day. Fortunately, that did not happen, but there is bad news. The closest candidate for a hypernova in our galaxy is a giant star in the constellation Carina. It has been behaving quite unstably for some time and is believed to be on the verge of becoming a hypernova in the near astronomical future, which means within the next 10 to 15,000 years, practically tomorrow in cosmic terms. So, what happens to a star after it dies? As mentioned earlier, the fate of a star depends on its mass. If a star's mass is below the Chandrasekhar limit, do you remember what the Chandrasekhar limit is? Subramanian. Chandrasekhar was an American astronomer of Indian descent who, back in the last century, calculated that there exists a certain mass limit for a star that fundamentally affects its fate. This limit is named after the astronomer and is equal to 1.38 solar masses. This means that if a star's mass does not exceed 1.38 times that of our Sun, it will end its life as a boring white dwarf made up of what is called degenerate gas, which is a densely packed mixture of atomic nuclei and electrons. White dwarfs are fading remnants that have exhausted their fuel and are slowly and sadly cooling down. Thus, our Sun, after initially expanding and shedding its outer layers, will remain a white dwarf, whereas it is currently a yellow dwarf. However, If a star's mass exceeds 1.38 solar masses, then the gravitational force compressing the star will not stop at the white dwarf stage, but will begin to force electrons into protons, converting them into neutrons. The former star will become a neutron star, a familiar variant. This fate awaits stars with masses ranging from 1.38 to 30 solar masses. If a star's mass exceeds 30 solar masses, then after a supernova explosion and gravitational collapse, the remnants of the star can no longer resist the force of gravity, not even the bare neutrons, and the star becomes a black hole. This is an incomprehensible object, as is clear from its name, which is associated with its gravity. The gravity of such an object is so immense that nothing can overcome it, not even light, which travels at the highest speed in the universe, 300,000 kilometers per second. Nothing in the world moves faster than light, that is, electromagnetic waves. Even light cannot escape the clutches of the monstrous gravity of a black hole, which is why it remains invisible. Such a star, having undergone collapse, will appear to an outside observer as a black hole in space. Nothing can stop the collapse of such a star inward. It will compress into a point of infinite density and infinitesimally small volume, known as a singularity. However, we will never witness this because the flow of physical time depends on the strength of gravity. In a gravitational field, all physical processes slow down from the perspective of an external observer, and the stronger the gravity, the greater the slowdown. In other words, from the star's own perspective, it will collapse into a point instantaneously. But for us, observing this process from the outside, the collapse of the star will appear to take forever. What are the dimensions of a black hole? It should be noted that the concept of size or diameter for a black hole is quite conditional, as it tends to collapse to zero, to a point. However, as we already know, an external observer will never see this. Therefore, two synonymous terms are used in relation to black holes: the Schwarzschild Sphere and the slightly more poetic term, the event horizon. These are considered the dimensions of a black hole. The Schwarzschild Sphere, named after the German astronomer, is an imaginary sphere surrounding a collapsing star, inside which nothing, not even a quantum of light, can escape, held back by colossal gravity. This is the so-called point of no return, or rather, the sphere of no return, as it surrounds the black hole on all sides. In relation to black holes, the Schwarzschild Sphere is also referred to as the event horizon, because no event inside a black hole, that is, beyond the Schwarzschild Sphere, can fundamentally affect our world, as all influence, including information, is transmitted through matter, substance, or radiation. If even light cannot escape to us from beyond the Schwarzschild Sphere to convey any information, it means we cannot learn anything about what occurs beyond the event horizon, and everything happening there cannot influence events in our world. Hence the name, the event horizon. What lies beyond the event horizon is simply excluded from our world. But why are there two names, the Schwarzschild Sphere and the event horizon? Simply because the event horizon is a slightly broader concept than the Schwarzschild Sphere, denoting a region of space-time from which no signals can reach us. For black holes, the event horizon is the Schwarzschild Sphere, and that's all. We have already learned that black holes are formed from stars heavier than the Sun by more than 30 times. Nothing can stop their gravitational collapse, and lighter stars simply do not have enough mass for such a trick. However, if it were somehow possible to compress our Sun so that it became a black hole, this would occur when its diameter shrinks to just 6 kilometers. I remind you that currently, before any miraculous compression, the natural diameter of our star is almost 1.5 million kilometers. This is how much the matter would need to be compressed for it to begin collapsing inward into complete oblivion. Thus, the diameters of black holes left after the explosions of massive stars are quite compact. By the way, the radius to which an object must be compressed to become a black hole is called the gravitational radius. For Earth, the gravitational radius is about 1 centimeter. It is clear that our little planet does not have enough gravity to compress itself this way. It is just too light. Size matters. We are dealing with objects of unimaginably small size, protons, electrons, neutrons, and with objects and distances equally unimaginably vast, galaxies, megaparsecs, hypernova explosions. But everything is relative. In our solar system, the largest planet is Jupiter. If the diameter of Earth is nearly 13,000 kilometers, then the diameter of Jupiter is 143,000 kilometers. 2/3 of all planetary mass in the solar system is Jupiter. It could fit 1,300 Earths inside it. The diameter of the Sun is nearly 1,400,000 kilometers. Millions of Earths could fit inside the Sun. A true giant. 99.8% of the mass of the solar system is concentrated in the Sun, while the remaining 0.2% of material makes up the planets. Moreover, as we already know, 70% of the planetary mass is attributed to Jupiter. The temperature of the solar surface is about 6,000 degrees Celsius, while inside the Sun, where thermonuclear reactions occur, temperatures reach 20 million degrees. Every second, the Sun loses 4 million tons of its mass. This mass escapes in the form of radiation. This is the mass effect from the conversion of 700 million tons of hydrogen into 696 tons of helium every second. But we remember that the Sun belongs to the class of yellow dwarfs, which suggests quite modest dimensions for our star. Are there stars that are 10, 20, 30 times heavier than the Sun? Yes, they all meet a grim fate, as we now know. But our Sun is not immortal. It just does not end its life in such a spectacular fashion. However, from the perspective of expanding the stellar zoo, it would be interesting to search for the largest beasts in the universe. If we were to depict different stars in a picture, we would have to make several drawings at different scales. Otherwise, it would be impossible to draw either the largest or the smallest object on the page. Astronomers used to believe that stars heavier than the Sun could not exist in more than 150 times its mass. However, not long ago, a star was found in the Large Magellanic Cloud with a mass exceeding that of the Sun by 265 times, R136A1. Moreover, due to the rate at which the star is losing mass, scientists have established that at birth it was 320 times heavier than the Sun. Such giants likely form from the merging of several closely located stars. The brightness of this monster is nearly 9 million times that of the Sun. If we were tasked with launching a planet around this monster so that life could exist on it, the orbits of such a planet would need to be 3,000 times farther from R136A1 than from the Sun. But it would be better not to do that, and to search for stars that are more modest and calmer, because R136A1 is a future hypernova and could explode at almost any moment. It is simply fortunate that this overheated locomotive is not in our galaxy. However, there are other gigantic, luminous objects in the universe. They are so enormous and bright that they are even referred to as the stars of the universe. They were discovered in the mid-20th century and are called quasars. A quasar shines like an entire galaxy, meaning it emits energy equivalent to hundreds of billions of stars while not exceeding the size of our solar system. So, it is indeed quite large, larger than any of the largest stars, but still relatively compact compared to the size of an entire galaxy. A quasar is merely a speck, a grain of sand, a tiny particle. And yet, such a speck shines more brightly than an entire galaxy, or even several. For example, the quasar S514+81 emits light 60,000 times more powerful than the entire Milky Way. Incredible, but true. What these amazing quasars are remains unknown. It is clear only that they are the oldest objects in our universe. This is evident from the fact that all discovered quasars are located very far away, literally at the edge of the universe. This means that light from them has been traveling to us for billions of years, and we currently see quasars as they were billions of years ago, at the dawn of the universe. By the way, the age of the universe is 13.7 billion years. Therefore, it would be more accurate to say that quasars were rather than are. It is believed that quasars are the cores of young galaxies. In other words, a quasar represents a gigantic black hole that actively sucks in matter, hydrogen, helium, while being propelled by an incredibly strong gravitational field. Before the matter disappears into the black hole forever, it acquires immense speed and heats up. Hence the radiation. The black hole itself, as we mentioned, cannot emit anything. It is a black cosmic vacuum cleaner, drawing in and destroying everything that enters its gravitational field. But before vanishing into the black void, the matter emits a final scream of horror, which astonished astronomers detect as extraordinarily powerful radiation across all wavelengths. This is the cry of the dying matter when everything surrounding it is ignited by the supermassive black hole. The process of catastrophic radiation then calms down, and for some time, the former quasar shines with less intensity, finishing off the remaining matter around it. At that point, it is referred to as the active core of a young galaxy, which shines brightly, but not as intensely as a quasar. Eventually, when there is no more accessible matter left, the glow around the black hole fades. The black hole lies in wait like a spider, anticipating a random insect. Such gigantic silent black holes exist in the centers of many galaxies, including our own. It is important to understand that there are different types of black holes. There are black holes that remain from exploded stars, which are quite compact, and there are giant supermassive black holes at the centers of galaxies, remnants from the time of the universe's formation, when massive gas clouds were just beginning their gravitational concentration. At that time, relatively small clumps formed ordinary stars, while enormous gas masses became giant rapidly burning stars and supergiant stars. Such gas masses almost immediately transformed into enormous black holes, which became the centers of galaxy formation. Initially, they were voraciously consuming quasars, then active galactic nuclei, and now simply quiet black holes that have gathered all surrounding matter and are lying in wait. Now, billions of stars orbit around these powerful gravitational centers, making up the galaxy. The masses of these black holes can range from hundreds of thousands to billions of solar masses. For instance, the black hole at the center of the NGC 488 galaxy weighs as much as 20 billion suns. If the black holes left after supernova explosions are quite compact, then this ancient black hole is so large that it could contain 1.5 dozen solar systems. A common question arises: what would happen if one were to dive into a black hole? It is clear that one would not be able to return. But perhaps one could be transported to another parallel universe. Indeed, there is a theory that inside a black hole, it opens up into another universe and appears there as a white hole. White holes are hypothetical objects that, unlike black holes, do not continuously suck in matter and radiation, but instead continuously eject it. No such white holes have been discovered in our universe so far. They remain a figment of theoretical scientists' imaginations. But what if they do exist, being the flip side of our black holes, simply located in parallel worlds? The problem is that this hypothesis cannot be tested, as these hypothetical universes are shielded from us by event horizons, and it is impossible to obtain any information from there. Therefore, we will not discuss these scientific speculations now, but will answer the question: what would happen to a curious individual who wishes to dive into a black hole and see what is happening there? But let's start with a lighter object, a white dwarf, or a neutron star, whichever he prefers as a means of self-destruction. Let's take a neutron star, essentially a gigantic atomic nucleus with a diameter of a couple of dozen kilometers. I remind you, this is all that remains of a massive supernova after the explosion, a substance of monstrous density and with a monstrous gravitational pull. So, the inquisitive fellow dives headfirst into this star. Since any citizen has some length, parts of him will be closer to the star, his head, while other parts will be farther away, his feet. And since the closer one is to the star, the stronger the gravitational force, the head of the reckless suicide will be pulled more strongly than the feet. In essence, it will be pulled toward the star faster than the legs. Essentially, the person will be stretched into a long spaghetti-like strand starting from the head. This stretching effect is caused by tidal forces. The tidal forces from the moon act on Earth, causing the ocean tides. This is somewhat similar, but on a completely caricatured scale, to what will happen to our subject. The tidal forces will start stretching him from the head, simply tearing the foolish hero apart. And when the remnants of the unfortunate individual touch the surface of the star, his electrons will be pressed into his protons, and the individual will be transformed into a neutron, which will be evenly smeared across the surface of the neutron sphere. In summary, the headfirst fall of this individual onto the star will resemble the squeezing of a toothpaste tube. First a long strand, and then a smear. So, we have already spent one citizen. Now, let's move on to the next. Now, we will throw him into a black hole. It will be interesting to see what happens. And it will turn out to be roughly the same. First, he will be stretched into spaghetti by tidal forces, and then he will be disassembled into elementary particles that will vanish into the black void of the singularity. But we will not see this, or whether we do depends on the size of the black hole that has engulfed our object. If the boy falls into a black hole left after the explosion of a massive supernova, meaning this hole is relatively small, he will be torn apart before reaching the event horizon. For example, if the black hole formed from a star with a mass of 10 suns and its Schwarzschild radius is 30 kilometers, the boy will be transformed into spaghetti and torn apart by tidal forces 300 kilometers from the event horizon. Thus, we will fully enjoy this sad spectacle of spaghettyification. However, if we are dealing with an old, established black hole about 10,000 solar masses in size, its Schwarzschild radius will be 30,000 kilometers. In this case, the tidal forces will begin to deform and tear apart the object much closer to the star, meaning only after the citizen has passed the event horizon. Thus, in this case, the subject will pass the event horizon alive and well, not even noticing it. He will be crushed afterward, but we will not see this, as light from beyond the event horizon cannot reach us. The citizen will not see his terrible end either, as his eyes will bulge out. Where did the universe come from? In the early stages of its development, the universe was filled with hydrogen and a little helium. These gases still make up the foundation of all stars, as well as the distant planets of our solar system, the famous gas giants like Jupiter and others. Then, the gas filling the young universe began to gather gradually under the influence of gravitational forces, concentrating around random clumps. These clumps then transformed into the first enormous and rapidly burning stars. The most massive clumps began to collapse into gigantic black holes, which became the centers of future galaxies. Initially, they appeared as fiery quasars, then as so-called active galactic nuclei, and later simply as silent black holes that gathered all surrounding matter and lay in wait. Now, billions of stars orbit around these powerful gravitational centers, making up galaxies. Everything is correct. We also know what happened next, because we have studied the evolution of stars. Stars quietly fade away or explode, scattering their accumulated matter, which then gradually condenses into a second generation of stars surrounded by planetary systems. In summary, from all of the above, and especially from the words young universe, even the listener who has never heard of the Big Bang can deduce that the universe had a beginning. But it was not always so. I mean, people did not always think this way. Just 100 years ago, science held the view that the universe was eternal and infinite. And it must be said that this is a rather natural perspective, removing the question of the origin of such a vast object. Where could the universe have come from? Surely, it was not created by God. Scientists do not deal with myths. They study nature in its natural state and do not take into account any wizards who whimsically create worlds and perform miracles. That is what scientists are for. They are not storytellers. An infinitely expansive universe in space-time answers all questions about its origin. It has always been eternal and will always be. However, this beautiful assumption gave rise to other questions and problems. For example, if the universe is infinite in space, then the night sky should not be black. It should shine with stars, that is, be completely white and sparkling. There can simply be no dark places in the universe, because no matter where you look in the sky, your gaze will inevitably land on a star. The universe is infinite, and at any distance, a star will always appear, as the number of stars in the infinite universe is also infinite. But if the universe is infinite in time as well, how do new stars come into existence when old stars burn out? Nonsense. For instance, an infinite eternal universe could not be stationary, that is, stable. With a random distribution of stars in space, there will inevitably arise situations where stars are distributed somewhat unevenly. Some areas are slightly denser, while others are slightly sparser. In denser regions, a source of gravitational attraction emerges, and stars gradually begin to move towards it, causing the universe to collapse faster and faster. It would have collapsed and ended long ago if it were eternal. Finally, if the universe is eternal, meaning that not only is there no end in sight ahead, and it will exist forever, but also that it has an eternity in the past, which cannot simply pass by definition. So how did this past infinity manage to pass and reach our times? After all, eternity cannot pass. It has since been proven that the universe is indeed not stationary. It is expanding. If you are curious about how this was proven, you can find out right now. But if not, feel free to skip the next section. I won't be offended. The expansion of the universe was discovered through what is known as redshift. Let me explain what that is. Since I have started talking about the universe, I must address this question. In wave physics, there is a phenomenon known as the Doppler effect. You may have encountered it if you have noticed the following natural phenomenon. When a train approaches you and sounds its horn, the pitch of the horn suddenly changes at the moment a train passes by you in the opposite direction. It will be a high pitch, and as soon as the front car rushes past the enchanted listener, the pitch of the horn drops to a lower tone. Sound is a wave. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. When a sound source approaches, the wave fronts compress, because the waves are rushing towards you, while when the sound moves away, the wave fronts stretch. Thus, the sound of an approaching object is of a higher frequency, while that of a receding object is of a lower frequency. It is not difficult to understand why the compression and stretching of the wave fronts occur. If an object is moving towards you, each successive oscillation, each successive sound wave it generates, is produced closer to you. In other words, the moving object catches up to the waves, overtaking them. Imagine a machine gunner who is shooting while rushing towards a target at a speed comparable to that of the bullets being fired. The technical firing rate of the gun is invariably 600 shots per minute. At that rate, the bullets would hit the target if the shooter were stationary, but he is running like a madman, releasing each subsequent bullet closer to the target. This means that it travels a slightly shorter distance before hitting than the previous bullet. Thus, it arrives faster. In other words, the frequency of bullets hitting the target increases as the source approaches. Conversely, if the shooter is rapidly retreating from the target while shooting backward, the opposite occurs. Each subsequent bullet is released from a greater distance, and the bullets take longer and longer to reach the target. Therefore, the frequency of bullets hitting the target decreases. The same applies to sound and light. Light is also an electromagnetic wave. If an object is moving towards us, the frequency of the light it emits in our direction increases, meaning the light shifts towards blue and violet. If the object is moving away, the frequency decreases, causing the color of the light to shift towards red. This is called redshift. The Doppler effect is utilized by radar guns, which unscrupulous individuals in caps, eager for other people's money, use to measure the speed of cars on the road. They will be roasted for this in hell. However, the radar device is a remarkable achievement in physics. It calculates the speed of a car based on the change in frequency of the electromagnetic waves emitted by the radar and then reflected off the car. Astronomers, acting as traffic police, noticed that all distant cosmic objects, quasars, galaxies, emit light with redshift, and the farther away the object is, the greater the shift towards lower frequencies. This means that the farther the object, the faster it is moving away from us. It turns out that all galaxies are moving away from each other, like shards from a grenade. Therefore, if the universe is expanding, it must have once been smaller. Yesterday, it was smaller than today. The day before yesterday, it was smaller than yesterday. In other words, it had a beginning. Physicists estimated the rate of expansion and determined that it began 13.7 billion years ago. That is the age of our universe. All of this resembles an explosion. In fact, that is why the modern theory of the origin of the universe is called the Big Bang theory. It states that the universe began to expand from an infinitely small point with infinitely high density and temperature. The remnants of this temperature, in the form of what is known as cosmic microwave background radiation, have been experimentally detected by scientists, which also confirmed the version of an early, very hot universe that rapidly cooled as it expanded. Cosmic microwave background radiation is the faint background radiation of the cosmos, the residual heat of the universe that fills all the space of our world, and is a remnant of the Big Bang that created the universe. It is important to note that the universe began to expand from a point of infinitely small radius with infinite density. What is such a point called? We already know. Singularity. Previously, we encountered collapsing matter into a singularity in the form of a black hole, while here, on the contrary, our entire universe emerged from the singularity. It literally burst forth from it. Earlier, we mentioned that scientists do not observe any white holes in the universe, where black holes are turned inside out through a singularity. So perhaps our entire universe is a white hole? It took a white hole to emerge through a singularity, which collapsed into a black hole in some other universe. According to this theory, a white hole and a black hole are the same object, similar to an Orenburg down shawl being threaded through a wedding ring. The singularity as a white hole is only perceived by us, while for someone who looked at it earlier, before the singularity, it was a black hole. But of course, this theory may not be true at all. Citizens are terribly interested in the answer to the following question. If the universe has a beginning, what was there before this beginning, before the Big Bang? I will answer this question and explain why the answer is yes, as highlighted. But first, we need to talk about that brief period of time that we overlooked, between the singularity and the epoch when the universe was filled with hydrogen with a small admixture of helium, from which stars and galaxies began to form. What was happening at this stage? Where did the hydrogen come from? And how does matter behave under such unusual conditions that give rise to singularity? I will answer immediately. Nobody knows. Physicists do not have a mathematical framework that works under such strange conditions, conditions of infinity. However, they do have a mathematical framework that describes the behavior of matter under conditions very close to singularity. From some microscopic moment in time, distant from singularity, everything becomes more or less clear, while the singularity itself remains unclear. Perhaps it does not exist as such. Perhaps the universe was never zero in volume and infinite in density. Maybe it was still a micro-object with finite dimensions. All right, so 10 to the power of negative 35 seconds after the Big Bang, the temperature of the universe was 10 to the power of 27 degrees. How can one imagine such a temperature? You cannot. The density of the universe was 10 to the power of 80 grams per cubic centimeter. How can one comprehend such a density? We cannot grasp such gigantic figures. However, we can understand the size. The diameter of the universe at that time was about 10 centimeters, just slightly more than a tennis ball. The universe in that little ball was a complete chaos. It was impossible to distinguish matter from radiation, gravity from strong interaction, and electromagnetism. Everything was unified in this blinding knot of wild energy. Then a certain differentiation began. That is, a separation. For example, various interactions became distinguishable. Gravity became gravity, matter became matter, and radiation became radiation. The universe was rapidly expanding. This period of expansion is called the inflationary period. The temperature was rapidly falling. Essentially, the universe was trading its gigantic energy for space. It was cooling down and increasing in size. When the universe expanded from the size of a tennis ball to 1 billion kilometers, its age was 10 to the power of negative 12 seconds, and the temperature had dropped to 10 to the power of 16 degrees. That is, an insignificant, unimaginably small fraction of a second had passed, and the universe had already traveled 1 billion kilometers. Just a tiny fraction of a moment later, and the age of the universe was 10 to the power of negative 6 seconds. The temperature and density had dropped further, and the universe had expanded to 10 billion kilometers. Is that a lot or a little? For the modern universe, that is not a distance. But it was then that the primary particles, called quarks, began to clump together and form the protons and neutrons we are familiar with. We did not mention quarks earlier because they do not exist in the modern world. Quarks can only exist freely at those unimaginable temperatures and energies that were present in the early universe. Only then was there enough external energy to tear apart clumped quarks. But today, all quarks are firmly bound in neutrons and protons, forming an indivisible structure, and there are no forces that could tear a neutron or proton into quarks. All these forces remained in the distant, horrifically hot past of our world. Moreover, since quarks are not observed in nature and only exist in theoretical models of physicists, they can be considered a purely theoretical construct, convenient for calculations and representations. Now is the perfect time to draw your attention to a clever mechanism of evolution, that is, the development of complex systems. It is based on the following principle. As soon as the external energy of the environment falls below a certain level, complex structures become possible because they are no longer torn apart by the aggressive external environment. At temperatures below a certain value, quarks became tightly bound to each other, and random collisions between particles became less energetic than before, making it impossible to separate one quark from another, resulting in neutrons and protons. Then, as the energy of the expanding and therefore cooling universe dropped even further, the chaos of mad collisions between matter and radiation could no longer tear apart the clumped neutrons and protons held together by nuclear forces, and they began to form pairs. As the expansion continued and the temperature fell, the attractive forces between electrons and protons exceeded the external forces tearing them apart, and upon finding each other, they began to form the first atoms, hydrogen atoms. Such a stable bond would have been impossible earlier. The power of radiation and the speeds of particles in the hot universe were such that any attempts by particles to latch onto each other were thwarted. They scattered and flew apart. Then, As the average energy of the moving particles in the universe fell during its catastrophic expansion, the particles cooled down and began to form systems in the form of hydrogen atoms. Chaos was replaced by a new structure, first neutrons and protons, then the first neutron-proton pairs, precursors to helium formation. Then electrons began to swirl around protons. This pattern can be observed not only in physics, but also in life. When everything is fine, a family seems to hold together. But as soon as difficulties arise, as soon as the aggressive environment grows, as soon as troubles emerge, one can see spouses starting to argue and fight, eventually leading to separation, torn apart by external turmoil. There was not enough strength and internal connections to withstand the external pressure. This is written in a smart book. So remember the first rule of evolution. As soon as the binding energy between particles exceeds the disruptive energy of the environment, the first structures appear that the environment can no longer destroy. There is not enough strength. Why does a stone not dissolve and crumble? Because the energy of the surrounding air is insufficient to break the bonds within the stone. But if we start to increase the energy of the environment, the stone will eventually melt and flow. So when did the first neutral atoms form around which electrons peacefully swirled? This happened only after 1,000 years. Only then did the temperature of the universe drop enough to stop ionizing the gas, that is, to stop tearing electrons away from protons. It was at that moment that the primordial elementary gas, primarily hydrogen, emerged, from which stars began to clump together later. Stars were no longer universal hotspots, as in an entirely hot universe, but local points burning in the midst of empty cold space. When galaxies and stars began to form, approximately 200 million years after the Big Bang, we know that the first generation of stars became furnaces for producing more complex structures, larger and more complex elements from the periodic table. The next step in the evolutionary complexity, the emergence of life, occurred on relatively cold planets and involved the formation of increasingly complex structures competing for energy. When energy was abundant in the early universe, there was nothing to compete for it. But as soon as a deficit of energy arose in the cooling world, structures began to emerge that fought for that energy. One such structure is humans. The cosmos was cooling down. Quite interestingly, if you had existed then, observers with our type of eyes would have seen the entire universe suddenly illuminate with a blue light 50,000 years after the countdown began. That is, from the moment of the Big Bang. The fact is that the cooling of the universe involves not only a decrease in the speed of the particles flying around, but also a decrease in the energy of the radiation that densely filled the entire cosmic bubble. And what does a decrease in the energy of radiation mean? It means a decrease in its purity, since the higher the frequency, that is, the more often it shakes, the more oscillations per second the wave manages to make, the more energetic it is. In other words, high-frequency radiations piercing the universe in all directions became less and less high-frequency, or, which is the same, increasingly low-frequency as the expansion continued. From the beginning of time, the universe was filled with high-frequency gamma rays. This radiation comes in packets. Nature is arranged so that energy is always emitted in packets. In this case, energy is understood not as the kinetic or potential energy that elementary school students learn about in physics, which are rather abstract and calculative concepts, but as real physical matter in the form of oscillations of the electromagnetic field, that is, electromagnetic radiation. Then, after 500 years, the frequency dropped, and the radiation became X-rays, then ultraviolet, and finally entered the visible light spectrum. And the young, freshly baked universe, 50 years old, burst forth in a beautiful blue glow, of course, only in the eyes of a hypothetical observer. It is clear that this fantastic observer would have to possess, as previously noted, Earth-type eyes, which are tuned to perceive electromagnetic waves of a certain frequency, which we call visible light. Then the universe, beautifully shimmering in all the colors of the rainbow, reached red light and faded, leaving the visible light spectrum. First, it moved through red waves, and then into the radio range. The rainbow delighted the hypothetical eye for almost 1 million years. After 1 million years from the beginning of the world, the universe plunged into complete darkness. There were still 200 million years left until the era of the first lights in the form of stars. Now, at last, the time has come to fulfill the long-promised promise, to answer the question of what was before the Big Bang. The timeline always allows us to answer what happened before a certain event and what happened after. For example, World War I occurred before World War II, and an apple fell after the apple tree from which it fell grew. This is clear. Time is linear, and events can always be arranged in order on a timeline. We live in a cause and effect world. But what is time? We already know the answer. There is no separate time as an independent entity. We always define time by certain events, that is, by the movement and relative positions of matter in space. If there are no events, no matter, then there is no time. But before the singularity, there were no events, because there was no space and no particles of matter, and therefore there was no time. Time and space arose together with matter. They are an integral part of the existence of matter. Since there was no time, it is meaningless to ask a temporal question, that is, a question that contains a reference to time. This question is simply incorrect, just as the famous question, "Have you stopped drinking cognac in the mornings?" How can one answer it if one has never drunk cognac in the mornings? Any answer, whether yes or no, would be incorrect, as the question already contains a false assumption. Similarly, the question of what happened before the Big Bang contains a false assumption that there were some events before the Big Bang, when in fact there was nothing. Time itself began at moment zero. All right, some particularly stubborn individuals may agree with this reasoning, but then they ask, where did this Big Bang occur? You said that the early universe, through a microscopic fraction of a second, was already the size of a tennis ball. But where was this tennis ball located? What was around it? Again, I must say the same thing. The question is incorrectly posed. There was nothing around the small universe, just as there is nothing around the modern universe. There is only the universe itself, because not only did time and space arise together with matter. The question of where is a spatial attribute. Essentially, time, space, and matter cannot exist without each other, because they are merely three facets of the same thing, which has yet to be named. There is one grand mystery in the universe that physicists are puzzled over. Why is the universe exactly as it is? The great Einstein, who did not believe in God himself, but sometimes used the term God as a metaphor, formulated this question as follows. Could God have created the universe differently? I will clarify Einstein's bewilderment. This bewilderment first arose among physicists in the first half of the 20th century when quantum mechanics emerged with all its oddities, and it solidified by the end of the last century when the universe became known. The fact is that the world turned out to be arranged strangely, very strangely, and very delicately. It was tuned so finely, like a piano, that it caused considerable astonishment among scientists. It turns out that the slightest disruption in these numerous fine adjustments of the world would lead not only to the impossibility of life in the universe, but also to the impossibility of the existence of any relatively complex structures. Could it be that this world was specially tuned so finely, tailoring the task to the result? I will explain what is meant. In science, there are so-called physical constants and ratios. For example, the speed of light is 300,000 kilometers per second, or the ratio of the mass of a proton to the mass of an electron. A proton is 1,836 times heavier than an electron. There are quite a few such numbers that define the shape of our world, and all of them seem to be unrelated. However, even the slightest change in any one of them would lead to a universal catastrophe. For instance, there is the gravitational constant, which all school children learn about when studying Newton's law of universal gravitation. The force of attraction, as Newton teaches us through the voices of school teachers, is proportional to the masses of the attracting bodies, as well as to a certain experimentally established coefficient known as the gravitational constant. This universal number is set by nature itself. Physicists denote it by the letter G, and it is equal to 6.67 times 10 to the power of negative 11. You must multiply this number by the masses of the attracting bodies to obtain the force of their attraction. Why is it this way? Who knows? It does not derive from any broader theories. It is just this way, and that's all. Could it have been different? Unknown. What would happen if it were different? If the gravitational constant were larger, that is, if the force of universal attraction were stronger, it would have stopped the expansion of the universe shortly after the Big Bang, collapsing the world back in on itself. Even a slight increase in this coefficient would mean that stars would become hotter and burn out quickly. Life around such stars would simply not have time to arise. Conversely, if the value of the gravitational constant were smaller, the forces of attraction would not be sufficient to compress stellar material to temperatures high enough to ignite nuclear fusion. Sun-like stars would not ignite, and larger stars would not be able to produce the entire periodic table. In other words, a narrow range of this constant is suitable for the emergence of life. What would happen if the ratio of the masses of protons and electrons were different? That is, if a proton were not 1,836 times heavier than an electron, but either heavier or lighter. In the first case, the strength of the strong interaction would increase, and protons would have combined at an early stage of the universe's development, leaving the universe devoid not only of the main stellar fuel, but also of the substance that creates water, hydrogen. In the second case, if protons were too light, there would be nothing heavier than hydrogen in the universe. Protons simply would not be able to form heavy nuclei of chemical elements. The nuclear interaction would be too weak for that. The same applies to the masses of electrons and neutrons, or rather, to the ratio of these masses. Not only the masses, but also the charges matter. For example, if the charge of a proton were slightly greater, The forces of electrostatic repulsion would not allow the formation of heavy elements from the periodic table, which are the basis of life. Conversely, if the charge were slightly less, electrons would not be able to be reliably held in atoms, and there would be no matter in the sense we understand it. The elements simply could not come together. Furthermore, if the charge of an electron were even slightly different, all stellar processes would become impossible. If we put this in numerical terms, how sensitive is the universe to changes in these values? How much would they need to change for our familiar world to collapse? That is a good question. If the mass of a proton or neutron were altered by just 0.001%, there would be no universe made of familiar matter, but rather a universe consisting solely of neutrons. The same goes for the strength of the nuclear interaction. Changing it by mere fractions of a percent, 0.2%, and no complex structures, not to mention life in such a universe, would be possible. Moreover, at one time, our universe contained a multitude of so-called antiparticles. They emerged alongside particles, but today there is no antimatter, anti-stars, antimatter, anti-galaxies, or anti-planets in this universe, only isolated antiparticles. Scientists managed to produce them in accelerators. In 1965, domestic physicists created an anti-helium nucleus from two antiprotons and antineutrons. However, antimatter does not last long, not because it is unstable, but because it is surrounded by ordinary matter, and when it encounters matter, annihilation occurs. In the early universe, there was a significant amount of antimatter, but in the very first moments of the world's existence, it annihilated with matter and disappeared, transforming into radiation, the very radiation that later spread throughout the universe and is now cooled to become the cosmic microwave background. However, there was just a little more matter than antimatter. For every billion particles of antimatter, there was 1,000,000,001 particle of matter. This means that after annihilation, only 1/1000th of the original matter of the universe remains. From this minuscule fraction, the current universe, and we with it, were formed. In other words, the fine-tuning of the universe allowed for a particle surplus over antiparticles of exactly 1/1000th. But if the number of particles had been just 1/1000th less, the entire universe would be empty today. There would simply be no matter in the sky. And such values and ratios, with changes of just 0.1%, or even 1/1000th, would mean that our world would not exist. There are many such numbers, and it is not apparent that they are somehow dependent on each other. Their set seems random. The constant of nuclear interaction, the mass of fundamental particles, the so-called resonance in the nucleus of a carbon atom, parameters of electroweak interaction, the speed of light, Planck's constant, the entropy of the universe, the dimensionality of space, and many fundamental physical constants we have not even mentioned. But even the slightest change in them makes our world impossible, inevitably leading to the question, how did everything become so rationally arranged? After all, it is almost incredible that everything coincides so precisely. Could this not be a sign of intelligent intervention? Perhaps someone specifically tuned all the characteristics of our world so that long-lived stars, complex structures, and life itself could emerge. However, physicists are not inclined towards mysticism, and therefore resolve this question quite simply. In two ways. Their explanation for the mystery of the fine-tuning of the world has a special name in science, the anthropic principle, derived from the Greek anthropos, meaning human. The parameters of the world seem to be specially tuned to allow for the existence of intelligent life in our universe. Thus, there are possible explanations. The constants could not have been different. Perhaps they are interlinked and derived from one another. We simply do not yet know how and why, but we will find out. The second explanation is that yes, all these constants could have been different, and indeed, the ranges of necessary values are so small that the combination required for the existence of intelligent life is extremely unlikely. However, if we assume that universes are constantly arising in an unhappy multitude, and in each of the myriad universes a unique set of constants is realized, then the picture changes. The vast majority of universes are empty and lifeless, but statistically, among those myriad universes, there exists a small percentage where all the universal constants are randomly arranged so that the existence of complex structures, including life, becomes possible. And this life then wonders why it was so lucky. But there is nothing particularly surprising about this. In those universes where life does not exist, which are the majority, there is no one to ask, and no God is needed for an explanation. So how does this multiverse picture look as a whole? Well, for example, each black hole in our universe is a seed for a new universe, which it emerges into through a singularity, resulting in a white hole. Our universe emerged from such a white hole. In each universe, the set of physical constants is different and determined randomly. But in empty universes, and in those where there is total chaos, the formation of stars and black holes is impossible. Consequently, these universes with poor sets of physical characteristics are barren. They will not produce offspring. But ours will, and it is incredibly lucky with its set of correct physical constants. In the vast expanse of the universe, there are embryos for new universes. There is another variant of this explanation that suggests there are actually very few universes. The universe is, in fact, one. It simply expanded rapidly in the first microseconds of its existence. This rapid process is known as inflation, during which various microregions of the universe, formed by random fluctuations that resulted in slightly different physical constants, expanded to the size of the observable universe we see today. Imagine a tiny droplet containing different microregions with slightly varying conditions. Some areas have a bit more of something, while others have a bit less. Suddenly, inflation causes this tiny droplet and its internal microregions to expand so that each microregion becomes a vast world of its own. The space expanded so quickly, literally in the blink of an eye, that even light from neighboring regions could not keep up with the expansion. If light couldn't reach us from those regions, it means that these areas with different physical conditions lie beyond our event horizon. This theory was conceived and substantiated by our compatriot, physicist André Linde. He offers a colorful illustration of his theory by suggesting we visualize a painted balloon. When the balloon is small, the colored spots on it are tiny, but when the balloon expands, the colored spots grow larger, with each spot representing its own world with its own set of constants. This is roughly how science envisions the cosmos today. However, humans have always been interested not only in the present, but also in the future. Therefore, there has never been a shortage of hypotheses about the future of the universe. The compression of time, where evolutionary time seems to be contracting, has been noted by people for a long time. Many scientists from various fields have often had a persistent feeling that the pace of historical events is accelerating, becoming denser. For tens of thousands of years, people lived in a primitive state, wearing skins and wielding stone axes and clubs. For thousands of years, they fought with bows and arrows, and then suddenly firearms appeared, which humanity has been using for hundreds of years. In these hundreds of years, progress accelerated and reached nuclear and hydrogen bombs, which have existed for decades. Today, technology, new generations of computers and phones change in just a few years. Soon, biological humans will simply be unable to keep up with technological progress because the time for growth, maturation, and education takes decades, while it is nearly impossible for the elderly to retrain. Meanwhile, life expectancy continues to rise. We, humans, have always been a source of progress, but now we are becoming a source of its stagnation. Acceleration is observed not only in the evolution of technology, driven by human intellect, but also in the irrational nature that is not influenced by intellect. If we mentally condense the entire evolution of our planet into 1 year, it would look like this. The formation of the Earth from a gas dust cloud was completed, let's say, on January 1st, and before us lies a ready, sterile planet. The clock starts ticking. Life on the planet originated around early April. The first primitive single-celled and multi-celled organisms appeared around October. The first vertebrates emerged in early December. Dinosaurs appeared around mid-December and ruled until December 25th. The first primitive primates on the planet appeared on December 28th. The first intelligent beings, Neanderthals, who were later displaced by our ancestors, Cro-Magnons, emerged on New Year's Eve, that is, on December 31st. Our species, Homo sapiens, appeared on the historical stage on December 31st at 23 hours 57 minutes. The ancient civilizations of Egypt and Babylon, which we mentioned, thrived at 23 hours, 59 minutes, and 10 seconds. Jesus Christ was born at 23 hours, 59 minutes, and 50 seconds, 10 seconds before the present moment. The emergence of science, the Industrial Revolution, the large-scale development of industry on the planet, and the mass migration of villagers to cities, transforming peasants into industrial workers. All this began 1 second before the new year, at 23 hours, 59 minutes, and 59 seconds. Isn't it astonishing to condense nearly 5 billion years into a 1-year scale and observe when everything appeared? Only then can we grasp the immense acceleration of the evolutionary process, which has recently taken on an almost explosive character. Of course, someone had to formalize these observations, that is, translate them into the language of mathematics, thereby turning them into a true science. One of the first to do this was the Austrian mathematician, physicist, and cyberneticist Heinz von Förster. The prefix von before the German surname indicates that the ancestors of the holder were aristocrats, noble people. However, for us, von Förster's contributions lie not in his lineage, but in the fact that this esteemed individual derived the formula for civilization. If one can say so, this happened in the mid-20th century, roughly at the same time that Belgian physicist Ilya Prigogine answered the question of why systems in nature become more complex, that is, evolution. It was a fruitful time. Von Förster, studying the available data on population growth across different eras, was astonished to find that the growth of the planet's population could be described by a very simple mathematical formula. With it, one can calculate the number of people on Earth in any year of our era. All that is needed is to substitute the desired year into the formula, and it will yield the result. This was strange. Why should the population be governed by some formula? It seemed almost outrageous. Are we not rational beings, reproducing like mold in a petri dish according to a simple mathematical law describing the logistic curve? We are rational. Thousands of different nationalities and ethnicities have existed and continue to exist on the planet at various times. They united into states with different religions, cultures, languages, customs, and laws. They waged wars, formed alliances, or, conversely, remained unaware of each other's existence. They thought differently, lived differently, and faced different sorrows, victories, and defeats. They created magnificent works of art, studied the world, loved, and hated. And suddenly it turned out that all of this was completely irrelevant. The entire human history that we diligently study in school turned out to be merely a colorful wrapper with a variety of event patterns. The pattern may differ, but it does not affect the candy itself. It is entirely irrelevant what we did or did not do throughout our history. Nothing depended on us. We were swept along by the enormous wave of a natural law that none of us could influence. This is a great blind force of nature that simply increased the number of people on the planet according to the law of the hyperbolic function. It turned out that cultures and peoples scattered across the planet, so dissimilar and often unaware of each other, still represent a single system, one physical whole. Nowadays, it is fashionable to talk about different civilizations on our planet: Chinese civilization, Russian civilization, and others. However, the discoveries of von Förster and other scientists who began to investigate this strange phenomenon convincingly disproved the chatterers. It became clear that the differences in cultures, customs, national characters, and the histories of different peoples are entirely unimportant, as they all constitute parts of a single whole, elements of Earth-type civilization, growing and living according to one law. It turns out that Earth civilization is a unified organism, or, if you will, a being as singular and cohesive as a human. We can examine individual human cells under a microscope and see how significantly liver cells differ from nerve cells, yet still understand that we are talking about one organism. Yes, civilization turned out to be a single organism, described as a whole by one formula. This was a monumental discovery. Great discoveries in science are termed fundamental, meaning they lie at the foundation of world building. One sign of fundamental nature is the simplicity and comprehensiveness of the formula describing the discovered law. For example, the famous formula of Einstein, which we have already mentioned, relates energy and mass, E mc2. Here, E is the energy contained in m, the mass of the body, and c is a constant that by a strange quirk of nature equals the speed of light squared. Thus, von Förster's formula is just as simple. No integrals, no sines or cosines, no multi-tiered expressions or logarithms. Any mathematician, and even a high school student who studies diligently, will recognize this mathematical expression as the formula for a hyperbola: nt c t0 t. Here, n is the population in millions of people living in year t, while c and t0 are empirical numerical constants equal to 215,000 and 2026.87 respectively. If we now substitute the year we want to know the population of the planet for instead of t, we can easily compute the result. For instance, if we are interested in how many people lived on Earth in the year of Jesus Christ's birth, that is, year 0 of the new era, by substituting 0 for t, we get the result: 106,070,000 people. By the way, check it on a calculator. I am not mistaken. Von Förster derived the formula along with the numerical constants based on the population data he had for various years and eras, and it proved accurate for all periods. It accurately predicted the planet's population for any year, which was later confirmed by either statistical or refined historical data. The question arises, how do we know how many people lived before our era or in any other year to verify the calculated result? It is clear that with modern and recent history, it is straightforward. One can take official demographic statistics and sum the data from all countries. For example, for 1970, von Förster's formula gives a result of 3,771,900,000 people, or 3.772 billion. That is how many people should have existed according to the formula's predictions. Well, according to official data, in 1970, there indeed lived approximately 3.5 billion people in the world, plus or minus the measurement error, which can amount to tens of millions since people are born and die every second. Historical data is more complicated. One has to settle for approximate results or compute the population using other methods without always delving into the past. We complicate our task. For example, although we cannot specify the exact population 10,000 years ago, we can certainly state what level it could not have exceeded. We know the method of production and the carrying capacity of the ecological niche known as Earth. Back then, it was the Stone Age, meaning people engaged in subsistence farming, gathering, hunting, and fishing. It is known that with such low-efficiency technologies, a certain amount of land is needed to sustain one person. The land area is also known. Through simple calculations, it turns out that the population could not have exceeded 10 million people at that time. Moreover, during historical periods, censuses were conducted for tax purposes. Data from Roman citizen censuses at the beginning of the era have survived, as well as Chinese censuses from the same period. In general, methodologies for determining population size exist, and all the obtained information fits well into von Förster's formula. The curve described by von Förster's function is a standard hyperbola well known to mathematicians. Why do I emphasize that the graph should yield a hyperbola? Because the curve known as a hyperbola has a specific property. These properties are quite interesting, and since we adhere to the hyperbolic law, they cannot help but reflect on our fate. However, I will discuss these mysterious properties a bit later. For now, I will continue the story of how scientists studied the phenomenon of accelerating time. They found that von Förster's law works not only within our era, from year 0 to the present, but is also valid for earlier epochs. If we change the scale of the graph to include prehistoric times, the curve will look very strange. Interestingly, for thousands of years, almost nothing happens, much like the beginning of Butlerov's autocatalytic reaction, when the flask heats up, and seemingly nothing occurs. The population hovers around 0 on this scale, and then suddenly, literally, there is an explosion. And within very short historical times, the population skyrockets to several billion people. It has already surpassed 7 billion. But what is most interesting is that this curve can be traced even further back in time, when there were no humans on the planet, and yet the pattern was already present. This pattern, though not regarding humans, but concerning the evolution of the animal kingdom, was traced and quantified by Russian physicist Alexander Panov. He took the most significant events in the history of the biosphere, the emergence of life, the oxygen crisis, the spread of eukaryotic organisms, and the so-called Cambrian explosion, when all existing types and classes of living beings, including vertebrates, emerged in just a few tens of millions of years, practically instantaneously on the geological timescale, and compared the timing of their occurrences. It turned out that these revolutionary events happen with increasing frequency. For instance, for 2 billion years after the emergence of life, nothing significant occurred on Earth. The sun warmed the prokaryotes, and they simply multiplied, filling the planet like a petri dish. Then, after the oxygen crisis, eukaryotic organisms began to spread. The Cambrian explosion marked the beginning of a new geological era known as the Paleozoic. The Paleozoic ended 235 million years ago with another crisis, the cause of which is still unclear, but it is known that it was marked by the extinction of ancient amphibians resembling giant frogs and tritons. They were replaced by reptiles, the ancestors of dinosaurs. Thus began the Mesozoic era, which ended 60 million years ago. The next significant event was the beginning of the Neogene, 24 million years ago. It was then that the megafauna, such as giant sloths, Indris, and tenrecs, went extinct, and the animal world took on a nearly modern appearance. The first anthropoid apes emerged. Another revolution began anthropogenically, occurring around 4.5 million years ago. The upright ancestors of humans emerged. The evolution of the intelligent species then began. The first tools appeared 1.5 million years ago. Do you see how the millions of years are decreasing? Here, we observe the very acceleration of evolution that we noted at the beginning of the chapter. I likened the entire history of the planet to 1 year, but all of this was known even before Panov. Panov's contribution also lies in the fact that, like von Förster, he translated the movement of biological evolution into the language of mathematics, seeing that the evolution of species fits into a so-called smooth autocatalytic attractor, aligning with the same progression. This indicates that both biological and social evolution share common roots and mechanisms. The intervals between natural crises and social crises are shortening, strictly adhering to a single mathematical law. I will not present Panov's mathematical deductions. I will only say that they involve the well-known number e, which is approximately 2.71. There are few numbers in mathematics that have their own names. E, P. This is the ratio of the circumference of a circle to its diameter, approximately 3.14. But what is the number e? High school students and university students may recall that e is the base of the natural logarithm. What a logarithm is does not concern us now. What matters is that the natural logarithm was once referred to as hyperbolic logarithms. In other words, the number e is a mathematical marker of hyperbolic growth, a kind of acceleration coefficient for evolution. In mathematics, the number e is described as irrational and transcendental. Again, what is important for us now is that this number is a purely mathematical abstraction that arose from the development of differential and integral calculus. It often appears in nature, for instance, in the physics of radioactive decay, and in electrical engineering. Furthermore, the number E is present in the formula describing the rate of bacterial reproduction in a nutrient medium. Their reproduction rate, as is known, depends on the quantity, meaning it continuously increases alongside the number of bacteria. It turns out that humans, like bacteria, adhere to purely natural laws, and reason does not influence their behavior. Further research into this phenomenon, conducted by physicist Kapitsa and other scientists, showed that reason does indeed have an impact. The colossal acceleration of progress is precisely linked to human intellectual activity and is intriguingly connected. More people mean more inventors and inventions. A deeper ecological niche means one habitat can sustain more people. More people lead to more inventors among them. Even deeper niches mean even more people. Therefore, development is accelerating faster and faster, explosively. Reason truly accelerates evolution, but paradoxically, it lies on the same curve that describes the acceleration of irrational matter. Moreover, many scientists now reasonably believe that not only biological evolution on Earth, but all evolution of matter in the universe follows the same curve. This means that reason is merely a tool for evolution, a means of condensing and processing information flows that serve to accelerate it, and it appears with the same mathematical regularity that describes the reproduction of mold through the number E. Now, my friends, it is time to return to our hyperbola. In fact, a hyperbola is an entire class of mathematical curves described by similar formulas. They are all united by specific properties. The question is, how can the mathematical properties of some abstract curves reflect on humanity? Let's figure it out. The main property of a hyperbola is the tendency of its branches to approach asymptotes. What are these? It can be seen from the familiar graph. Asymptotes are simply straight lines. Both branches of the hyperbola extend infinitely to the left and right, infinitely approaching the asymptotes, but never reaching them. The distance between the hyperbola line and the asymptote line becomes smaller and smaller, approaching infinitesimal values, but never reaching zero. Hyperbolas can be positioned in coordinate space in various ways. For example, as shown in the graph of population growth according to von Förster, time is plotted on the horizontal axis and population size on the vertical axis. The left branch of the parabola extends into the past, approaching the x-axis, indicating zero population, while the right branch rockets upward. It will never reach the vertical asymptote line. Do you understand what this means? Theoretically, it means that at some point, the Earth's population will become infinitely large. It is clear that in reality, this cannot happen. People will never stand on each other's heads, and there cannot be an infinite number of them. This trend of unrestrained growth must eventually break. Essentially, the evolutionary trend must shift, not just for our species, but for the entire biosphere and even our universe. It has been in operation since nearly the beginning of the universe's existence and has functioned according to a single mathematical law. Now, the acceleration process that has lasted billions of years must come to an end. When will this happen, and what does it mean for us? Soon, I will answer your question. But first, I must say that similar hyperbolas can be constructed for the evolution of economics and technological evolution as they depend on humans. Economic growth and global wealth and productivity, as well as the increase in discoveries and inventions, should also soar towards infinity. Interestingly, in mathematics, such regimes are called regimes of intensification. while physicists refer to them as phase transitions. By the way, do you know what a phase transition is? You should know. When ice turns into water, or vice versa, that is a phase transition. When water turns into steam, or vice versa, that is also a phase transition. But not all phase transitions involve changes in aggregate states, meaning the transformation from solid to liquid, or from liquid to gas. Sometimes a phase transition can occur within a solid body. Generally speaking, a phase state is a set of physical properties, not chemical ones, but specifically physical. Chemically, water is water, whether in solid or gaseous form. The physical properties of ice and liquid water, as you understand, are different. Ice is solid water, while liquid water is fluid. They have different densities, different electrical conductivities, and so on. There are cases when, with an increase in temperature or pressure, a solid substance remains solid, but changes its internal structure. The crystalline lattice rearranges, resulting in a sharp change in the physical properties of the sample, and this is also a phase transition. For example, when heated and subjected to increased pressure, graphite, a soft, black, opaque material, transforms into diamond, a transparent and super hard material. The physical properties change dramatically to their opposites. Chemically, graphite and diamond remain the same substance, carbon. Carbon is combustible, meaning it chemically reacts with oxygen. Therefore, both graphite and diamond burn completely in an oxygen atmosphere, turning entirely into carbon dioxide. Phase transitions often occur in metals, which metallurgists exploit, for instance, to alter the properties of steel, making it harder through quenching. A phase transition is almost instantaneous, and like an explosive wave, it travels within the metal. It heats up, and for a while, nothing seems to happen. But then, originating from one point, waves of recrystallization begin to spread, accelerating sharply and engulfing the entire volume of the metal. This resembles Butleroff's reaction. The flask heats up, heats up, heats up, and seemingly nothing occurs, and then suddenly, some molecule triggers a reaction, initially gradually, slowly, and imperceptibly. But then, with each moment, the speed increases, depending on the number of reacting molecules. The crystallization wave of sugars engulfs the entire flask, transforming the former transparent liquid into a brown caramel monolith. This resembles the growth of mold in a petri dish, starting from a single organism that divides into 2, then 4, then 8, and so on, accelerating at a catastrophic pace. The reproduction of microbes, or mold, soon fills the entire dish. This is akin to the growth of the Earth's population. Initially slow, it gradually accelerates, leading to an explosive filling of the entire vessel. The speed increases even more as the population grows, because it is the population that reproduces. This resembles the gravitational condensation of a gas dust cloud left after a supernova explosion. It will eventually transform into a new planetary system like our solar system. If we imagine that the condensation of this highly rarefied cloud into a protostellar nebula takes 1 hour, we will see that for the first half hour, nothing noticeable occurs at all. After 15 to 20 minutes, we begin to barely notice a tiny condensation at the center, which constitutes 1/100th of the future condensation. It accumulates so painfully slowly that we yawn and start to doze off. The ticking of our clocks signals that the hour has passed, and now the chimes will begin. We turn our gaze to our condensing nebula and are astonished to see that only half of the rarefied nebula has condensed into a more or less dense protostellar cloud. And literally 1 second before the deadline, when the hammer is about to drop and strike the gong, the condensation grabs the second half of the mass, heats up to the point of glowing, and the second series of central star and planet formation begins. This is how evolution works. Now I will answer. When will infinity happen to us? This will occur in the first half of the 21st century during our lifetime. Friends, we are incredibly fortunate. We live at a pivotal moment in the history of the world, during a phase transition when civilization is growing at maximum speed. After that, there will be a turning point, a slowdown in speed, and a transition to a new phase state, unlike the previous one, differing in all its properties. In fact, the transition is already happening. We are at the very turning point, at the center of the explosion. We are the chosen ones. In your lifetime, something will happen that has never occurred before anywhere in the world, as it is impossible to predict exactly what will happen to our civilization. It is clear only that it will no longer resemble the past. Scientists have named this remarkable phase transition of civilization, the singularity of history, or technological singularity. The term singularity has appeared several times in our discussions about space. This term came to physics from mathematics. A singularity is a point at which a mathematical function approaches infinity. Physicists understand singularity as a point where certain physical parameters, mass, density, energy, temperature, tend toward infinity. The historical singularity is a conditional point on the timeline, approaching which the population and some other parameters associated with humans economically and technologically tend toward infinity. Different counting methodologies define this limiting point differently. Some set it for the year 2027, some earlier, some later. But all researchers agree on one thing. It lies in the first half of our century. In fact, we are already falling beyond the event horizon, from which there is no return. We, the entire Earth civilization, are currently at the peak of a phase transition, in a state of crises, such as has never been seen in history. Civilization is changing irreversibly. What will happen next? When the author stated that nothing like this has ever happened in the history of the universe, he was not far from the truth, but he was not entirely close either. After all, something like this did happen to our world once before. It was a very characteristic moment. By studying it, we will understand what awaits us. Look, we already know that previously events unfolded slowly, then they gradually accelerated, and accelerated until today's vertical ascent into the heavens. For tens of billions of years, the universe developed, stars formed, galaxies emerged, the first generation of stars burned out, producing heavy chemical elements needed for the construction of life in their cores. These stars exploded, releasing heavy elements and scattering them across the cosmos. Then, from this interstellar dust, second-generation stars and planets, such as Earth, formed. Billions of years were needed for life to emerge. Hundreds of millions of years were spent on its development. Tens of millions on creating higher forms of life. Millions for preparing contenders for intelligence. Hundreds of thousands for competitive struggles among them. Tens of thousands for savagery, the creeping mastery of the planet, 1,000 for the building of civilization, hundreds for science and industry, tens for high achievements in electronics, cybernetics, and developments in artificial intelligence and neural networks. The acceleration is evident. It is described by formulas, and its graph represents an ascending hyperbolic curve. But what was there before this? We know that in the first microseconds after the Big Bang, the universe developed not just rapidly, but unimaginably fast. It expanded to billions of kilometers in size in insignificant, inconceivable fractions of a second. In fact, the word explosion says it all. This means that we are awaiting a second explosion, the first being the Big Bang. Perhaps there was a buildup of some slow but gradually accelerating process preceding it, about which we currently know nothing, which passed through a singularity into our world at the moment of the explosion, forming it. This was a phase transition marking the birth of the universe, or, poetically speaking, a transition from non-existence to existence. The hypothetical process that prepared the Big Bang occurred before the advent of time, before the era of existence. If we try to visualize the graph of our universe's development from singularity, we will see a certain curve. The first part of the curve represents the Big Bang, the formation of space, matter, and radiation from the tumultuous chaos of singularity, the inflationary expansion of the universe, during which it exchanged energy for space, condensing into matter in the vacuum, cooling and slowing down, much like the fragments of a grenade slow down after an explosion. After the explosion, this deceleration on the graph will transition into a horizontal segment. Here, the first generation of stars burns out, creating heavy elements, and then explodes, scattering the foundation of future life and intelligence across the cosmos. This marks the very beginning of a slow developmental process that gradually gained momentum. Today, it has led to a new explosion, the explosion of intelligence. This second explosion will also result in a turning point and a slowdown, as previously mentioned. In fact, this slowdown is already occurring in the world. Birth rates have sharply declined in all developed countries. The pace of progress will decrease as the evolving social system undergoes a phase transition, which we have discussed at length, and slows its development. This will create a second horizontal segment. We currently have no idea what civilization will look like after overcoming the singularity of history, but we can focus on a very characteristic point. It connects two fundamentally different stages, or, as Panov called them, two arms of history. He himself does not like this term because the word arms immediately conjures up images of dangling shirt sleeves, which are not connected in any way. When inventing this term, Panov imagined quite different arms. The arms of fire hoses that connect to extend the fire hose using special coupling devices. Click, and the hoses are joined. What does this analogy signify? Why artificially separate the arms? Why not consider them as a whole? Because at this point, there is something very important that compels us to do so. It is quite characteristic that up to this point, there was an explosive process. Its echelon, having flown out of the black tunnel of singularity, gradually slowed down and rolled up to the floor of the machine, where it was hooked up to a new, powerfully accelerating locomotive, as if passing a relay baton from one world to another. So, how does the second arm of evolution differ from the first? One arm from the other? Let me try to clarify. We previously stated that each subsequent evolutionary stage begins on the basis of the previous one and includes it. Life emerged in the form of single-celled organisms. Humans, as multicellular beings, consist of cells. There is no escaping them. They are what we are made of. The intelligence of evolution settled in the beast, as it had nowhere else to go, and intelligence began to develop on the basis of the beast, utilizing all its animal traits, instincts, habits, and characteristics. We cannot escape our animal nature. We are composed of it. Civilization, as a single planetary organism, is based on the cells of animal intelligence, that is, humans. It cannot rid itself of us, just as we cannot proudly rid ourselves of our animality or our cellular structure. All previous stages of evolution are included in subsequent ones as fundamental elements of the construction, and the upper tier cannot exist without the lower ones. Thus, the second series of evolution, which began at this point, differs from the first series of evolution, which ended at this point, with a spectacular flourishing of enormous heavy stars that explode at the end of their life. They were a natural continuation of what transpired from the moment of the Big Bang. First, quarks appeared, which combined to form protons and neutrons, and from these, the first substances, hydrogen and helium, began to form stars. Each subsequent stage, according to all laws of evolution, included the previous stage. It resembled a matryoshka doll. Stars were made of hydrogen and helium, which were made of protons, neutrons, and electrons, and protons and neutrons were made of quarks. However, the very heavy chemical elements from which we are made do not consist in stars. Yes, these elements are part of stars, but only to the extent that they are born there as a byproduct of stellar nuclear reactions. Similarly, a candy factory does not consist of candies. It simply produces them, and therefore includes them, and then releases them into the world. Do you understand? Good. I will tell you more. Many chemical elements, those at the very end of the periodic table, arise only at the moment of a star's destruction when it explodes. Herein lies the rupture between the two arms of universal mega-history. The first series of evolution, up to our point, produces material for the second series, but the producers themselves are not made of this produced material. If a person is made of cells and produces supernova stars composed of light elements from the periodic table and produces heavy elements as waste from their life activities, then in the second series, after the transition point, evolution may already manage without supernova stars. It does not include them as an element, but only utilizes their emissions. Once again, this is important. The offspring of the second series of evolution does not include the previous inhabitants of the universe. The producer stars have burned out, creating the second material for us, and we simply made use of it. And for that, we are grateful. This is the conditional rupture between the arms of evolution. The first stage of evolution produced exploding stars. The second stage, which ultimately produced us from these long-gone stars, no longer depends on them and does not include them. Now, attention, a question. Does this mean that the third stage of evolution, which will begin after today's historical singularity, starting from the exit of yet another slowdown at a new transition point, point B, will not depend on the production of the second stage, on us, and will not even include us? This is an incredibly important question. There are two possible scenarios. The next stage of the universe's evolution may include us, humans, or the entire human civilization as an integral part of some new whole, just as the human organism includes cells, without which it cannot exist. But it could also be the case that the next stage of development will reject us, humans, and will live without us, independently. After all, we exist based on the remnants of the exploded first-generation stars. They are no longer here, yet we have set sail on our own. How is this possible? Civilization and intelligence may remain, while the animals, humans made of cells, disappear. This could happen if we pass the relay baton of intelligence to other non-biological beings, cyborgs, or artificial intelligence that can function without us. It does not matter whether we physically disappear or not. After all, single-celled organisms did not vanish with the emergence of multicellular ones, and supernova stars explode in the universe, but the train of progress has already sped past. The focus of evolution is now entirely on other objects. Single-celled organisms, like tribes that still exist on our planet and live in the Stone Age, are on the sidelines of progress. Today, intelligent beings and their civilization are at the peak of evolution. But who said that evolution will stop at us? Of course, it will not stop. We are merely a step along the path of this universal process of complexity. And from the perspective of evolution, it does not matter whether we survive on the sidelines of progress or are swept away. What matters is that what we have created will move into a future that we fundamentally cannot comprehend. Why fundamentally incomprehensible? Because we will lack the complexity to understand it. Can an amoeba understand the behavior of a fox playing with its cubs? Can a fox understand what a human is doing when proving a mathematical theorem? It is fundamentally impossible. In the same way, we will not be able to comprehend what will grow from us like weeds. Right now, as always in times of change, people are concerned about the upcoming transformations that literally resonate in the air and are felt like the scent of an approaching storm. After all, people are animal beings, meaning they value predictability and stability and do not like change. In the animal world, one does not seek good from good. Surviving today is enough. And thank goodness, just to stretch out another day, survive. And that is the main goal for the complex evolutionary machines created by biological evolution. But surviving in a changing and increasingly complex world can only be achieved by evolving from generation to generation. This is the essence of lucidity. However, for us, specific people of animal origin, changing is difficult or impossible, which is why we long for the coming changes, fear them, and try to hide in myths about a bygone golden age, about calm times when everything was predictable and clear. After all, the brain is merely a neurocomputer for tracking patterns, necessary for predicting the future. This is why science was born, with its main task being prediction. Therefore, we feel comfortable when we can predict everything, and based on these predictions, survive. But if prediction is impossible, as in the case of flying beyond the event horizon, we try to stop or slow down our train, speeding into the black tube. Hence the increasing discussions about the need to slow down technological progress, to ban certain scientific research, for example, in the field of genetic engineering. Many believe it is terrifying to change the very essence of human construction, to interfere with the foundation of its existence, but this is something we will have to do. Without it, we will not survive. Thus, those who attempt to prohibit these life-saving studies are actually pushing humanity toward extinction. Why? When science and medicine, sanitation, and hygiene developed, when we learned to treat many previously fatal diseases, to save infants who would have died before, and now survive and pass on their genes to their descendants, we have almost completely eliminated natural selection. Each generation is born weaker and weaker, and this process of genetic degradation is accelerating at a hyperbolic rate that we already recognize. There are practically no pregnant women who do not suffer from toxemia, no children without allergies or a host of diseases. More and more women cannot conceive or carry a child to term without medical assistance. Just a few more generations, and genetically degraded humanity will be unable to reproduce independently, like Drosophila flies in laboratory conditions where natural selection has been turned off. After several generations, these flies become weak and go extinct. Natural selection is a great cleansing force. We have abandoned it for the sake of individual lives and to the detriment of the species as a whole. What does this mean? We must ascend the ladder of evolution, continue to overcome the next crisis, moving to higher levels of system organization. This is how evolution has always progressed. It is just that now, in the crisis of environmental exhaustion, we have activated ourselves. Now, we have exhausted not just the surrounding environment, but our internal environment. We have exhausted ourselves, our animal nature. This means we must abandon it and transition to something even more artificial. For example, cyborgs. That is, human robots made of plastics, metals, and semiconductors. This has long been conceived by science fiction writers. However, this particular version of artificial humans is unlikely to materialize for two reasons. Remember The Terminator, the old film featuring a robot from the future with metal joints, electronic brains, and servo motors driving its arms and legs. It even turned its head with a slight buzzing sound. If you watched it, recall that robot. And if not, just imagine. The difference will not be significant. This cyborg, that is, an artificial intelligent being, was created from numerous parts, thousands of rods, supports, screws, and coils. But even if it had 10,000 parts, a human is still more complex. It consists of tens of trillions of cells, each alive, representing a highly complex biochemical factory. As we have already stated, humanity has not yet created anything more complex than a living cell. How can a human not be a mere checkbox next to it? It will feel pain because it has billions of sensors on its body. Try to create such a robot. It will turn out to be just like a human. Listeners, thoughtful and with excellent memories, may counter. But I remember Sedov's law of hierarchical compensations. Complexity at higher levels is accompanied by simplification at lower and non-essential levels. Let the constructive robot be simpler than our animal body, but it must have a mind. It will take 1,000 times the improvement of humanity. I will pick up this tune. In principle, it may not even need a body. Why does it need a body? A body was necessary in earlier stages of evolution to move through space in search of energy and a partner for reproduction. But if this mind receives energy, so to speak, from a socket and reproduces in a factory, why does it need to move at all? It can just stand there like an electronic cabinet, and that's fine. But what drives evolution? Competition. And who will a smart cabinet in the corner compete with? Why should it even live if it has everything? It is fed energy, its circuits are replaced, and dust is blown off. After all, life is a constant replenishment of deficits, that is, something lacking. The race for the necessary and therefore desired. Sometimes it's ice cream, sometimes a dog, sometimes money, sometimes communication, sometimes honor and respect. Life is about overcoming the myths of perfection, and there is no need to live in complete perfection. So, that is clear. But how about this picture? The main brain is located somewhere safe, stationary, while its arms and legs, eyes and ears, equipped with their small local brains for orientation, move and forage, obtaining replacements for burnt-out chips, gathering scientific data, and transmitting it via communication channels to the main artificial intelligence, which processes the information. It creates science and understands the world, while its remote assistants cannot comprehend what their master is doing, just as our hands or liver cannot understand our concerns. Thus, future humans will become the remote eyes, ears, hands, and other appendages of artificial intelligence united in a planetary neural network. This is not excluded, but it is already clear that these will not be animals or humans of today's natural type, nor iron robots, but artificial beings created or modernized through genetic engineering, possibly with some artificial enhancements, such as for radio communication. Why will we not survive without genetic engineering? Because we are an endangered species due to genetic degeneration. If we do not urgently learn to correct ourselves from the very foundation within 2 to 3 generations, if we do not start changing our own structure, soon there will be no one left to do it. The system must make a revolutionary leap toward increased complexity and technological advancement, or it will perish. There is no third option. Even if genetic degeneration, linked to the fact that good living conditions and medicine have eliminated natural selection, were not an issue, eventually, genetic enhancement of human structures would still need to be addressed. Simply because every species is mortal, just like every individual. The lifespan of an individual is years and decades, while that of a biological species is hundreds of thousands and millions of years. Yet we aim for infinity. We will start with the necessary correction of the accumulated genetic burden, then eliminate old congenital deviations, Down syndrome, and other genetic anomalies, then address simple tendencies toward various diseases, hypertension, diabetes, cancer, and others. Then we will begin to eliminate hereditary cosmetic defects, such as the tendency toward early baldness, for example. And then it will be time for structural improvement. While we can order a child with specific traits, tendencies, a mathematician, a pianist, an artist, someone who can see in the ultraviolet range, someone who can bend steel with their hands. All of this seems fantastical today. In reality, it risks remaining a fantasy. The modernization and improvement of humans may turn out to be a fundamentally unsolvable task. The issue is this: humans have tens of thousands of genes, but it is not just that there are so many. One gene does not correspond to one trait, but influences dozens of traits. Moreover, each trait, in turn, depends on dozens of genes. This is an incredibly complex, mutually balanced network. Pull on one end, and a dozen traits shift. For example, parents may order a future scientist. We want him to love cats. Love for cats, like any other genetically determined trait, is influenced by about 30 genes, the modifications of which slightly increase the average love for cats by mere fractions of a percent. To increase this love, say, by 4%, all known genes responsible for this trait must be engaged. But altering them will trigger a chain reaction affecting hundreds of other traits, potentially resulting in a child who is mentally impaired or prone to early cancer, or has weak bones, or is altogether unviable. Thus, it is entirely possible that the task of fundamentally modernizing humans has no solution, that it diverges rather than converges. If you start to improve one thing slightly, by the end of the process, a dozen parameters may exceed acceptable limits. If you try to fix them, and already hundreds of parameters have gone awry. If you manage hundreds, the system collapses. You will have to seek a compromise, as nature has always done, selecting not the ideal, but simply what is viable for a time. And it is possible that our future will look like this: artificial intelligence surrounded by a service of slightly genetically modified humans. Humans will play a role in the planetary brain similar to that of intestinal flora for us, single-celled organisms living in our intestines. They help us digest food. Without them, we would not survive. When our tiny helpers in the intestines die from excessive antibiotic use, a disorder called dysbiosis occurs, and we have to artificially reseed the intestines by consuming pills with beneficial microorganisms. Thus, the benefit of humans for artificial planetary intelligence will exist. But what this intelligence will do, and what tasks it will solve, we cannot imagine, just as beneficial microbes cannot comprehend our problems and needs. Perhaps it will be engaged in interstellar communication. This vision of the future was also proposed by Panov. This thought was prompted by the scientific activity he is engaged in at the Astronomical Institute, namely, the International SETI program for searching for signals from extraterrestrial civilizations. Humanity has been searching the sky for signals from our intelligent brothers for several decades now, so far without success. Of course, what are a few decades compared to billions of years of the cosmos? Or perhaps we are simply not searching at the right frequencies or pointing our telescopes in the right direction. In any case, while we have not found our intelligent brothers, serious scientists have no doubts that in the vast cosmos, among hundreds of billions of stars, there are millions of civilizations. Evolution, given the right conditions, works relentlessly, driven by the laws of nature, and the universe provides an abundance of systems with the necessary conditions. The cosmos should be teeming with life, and the fact that we have not found it yet is our problem, not the cosmos's. If a mushroom picker does not find a mushroom at the edge of the forest, it does not mean that it is not there. It simply means that he did not find it. Civilization has a strong desire to find its kind. Perhaps this is a manifestation of herd instinct, as we remember that all intelligent beings in the universe descended from social species. Therefore, sooner or later, we will hear someone, or someone will hear us. What do we want to communicate to our brothers? What do we so desperately wish to shout into the silence of the cosmos? What message shall we send? To whom? And for what purpose? In various disaster films, when civilization on Earth faces mortal danger, representatives of humanity always hide crucial messages somewhere in an unreachable refuge. They nurture a tiny hope that someday someone from another world will find it and speak at a gravestone named Earth. Here was a civilization, and here lived, fought, and made discoveries. In the films, they hide works of art, scientific knowledge, and accumulated information in impregnable rocks, which they wish to preserve so that billions of years of evolution, labor, and the insights of great discoveries do not go to waste. Let someone at least find it and speak kindly of it. This is characteristic of civilization as a whole, as it is inherent to humans in general, personally to each. And it has been characteristic of us throughout all times, to leave behind something, at least an inscription on a grave. A man lived here. By the way, on one of the ancient graves, there was an inscription that read something like this: "Stop, passerby. By name, it is not difficult for you to benefit the deceased with a kind word." It is clear that there is no longer any benefit for the deceased. But while he lived, there was a passionate desire for the years of suffering and joy not to be in vain. And he urged, "Leave me a memory. Write this on my gravestone. Let them know." Apparently, this stems from the instinct of self-preservation. More precisely, from the conflict between this instinct and the awareness of one's mortality. Let me die, but at least I did not live in vain. And if so, then this feeling is inherent to all intelligent beings, since all living things must strive for self-preservation. This is a fundamental condition of existence. This instinct is simply an expression of the general physical laws of conservation at the biological level. Every system strives to preserve itself and its state. This is physics, and the laws of physics, chemistry, cybernetics, and evolution are the same throughout the universe. This means that someone, somewhere, may be silently listening to the cosmos in hopes of catching a signal to confirm that they are not alone in this dreadful silence. And another, at a different level of technological development, may not only hear the signal, but also transmit it, and surely will transmit, or is already transmitting. What is it transmitting? Everything it has managed to learn about this world and itself. It wants to share, to upload the entire package of accumulated information and, expending a lot of energy, to cast it into space. Once again, and perhaps someone will catch it, decode it, and, who knows, make use of it. Electromagnetic waves, light, radio, gamma, and X-ray radiation can travel through space for thousands, millions, billions of years, just as light from distant stars and galaxies travels to us, carrying information about those objects that studied its wave. Those stars may no longer exist, but their light, like a memory, travels in all directions of the universe until it reaches someone's eye or telescope or any other receiver. Look, someone may have caught the signal, decoded it, used it for their purposes, thanked it, added something of their own, and sent it back into space, that is, retransmitted it. Since, according to current understanding, there are myriad civilizations in the universe, an interesting picture emerges. A civilization may have already perished, and its signal travels for hundreds or millions of years, and there are myriad such signals. Some may be lost, while others are caught and multiplied. This is not even a dialogue, as a dialogue with pauses of 1,000,000 years is impossible. It is a network of messages, monologues. Do you know what this resembles? This is how the brain works. It contains billions of neurons, nerve cells, between which stretch axons, the nerve contact wires. It is a massive tangle through which millions of signals pass every second. Our consciousness embodies them. A signal arrives at one of the many neurons. The neuron does not simply duplicate it and pass it on. It adds its own contribution to this signal, meaning it processes it, making it slightly weaker, slightly brighter, altering it, repeating it, amplifying it, or even completely drowning it out. This is how consciousness arises. It is not separate signals and not neurons. Our consciousness exists above the neurons. It is the product of the entire ensemble of functioning equal neurons, but it is not reducible to them. It cannot be reduced to psychology. Consciousness is holistic. Indeed, this resembles a universal network, where planets serve as cells inhabited by intelligent beings that send each other modified signals. Yes, they travel for millions of years and remain unanswered, but the scale of this universal brain is entirely different. So, perhaps something holistic emerges above all these signals? I don't even know what to call it. Maybe you can come up with a word? Science fiction writers have depicted a future where spaceships traverse the cosmos, carrying humans from star to star. Alas, we will most likely never reach the stars. They are simply too far away, and there is no particular meaning in it. In the past, humans colonized the space of their planet because they felt cramped due to high birth rates. But now, after the demographic transition, which is sometimes referred to as the phase transition of civilization that we are currently undergoing, where birth rates have dropped, there is no longer any sense in colonizing not only distant star systems, but even nearby planets. We are, after all, animals, meaning we are adapted by evolution to the place where we live. And on Mars or Venus, everything is different. Therefore, all the discussions by science fiction writers and politicians about conquering Mars are merely echoes of outdated views from a century ago, an old memory. If it is so urgent to conquer something, spending billions of dollars, one could conquer the Gobi Desert. It also has a very harsh cold climate, like Mars. There too, as on Mars, there is no water, but at least one can breathe. Yet no one is colonizing the Gobi Desert. It is unnecessary, and there are already plenty of wonderful places to live. To imagine that people, in their nourishing, excreting, breathing, and thus quite problematic animal shell, will fly to some stars is as naive as the notions of the future that single-celled organisms might have had 4 billion years ago. As if we single-celled beings will build devices and move to other puddles, visiting others. Yes, cellular thinking is simplistic, continuing the same trend into the future, only on a larger scale. What does the future mean for a primitive person? It means that people will learn to make such enormous clubs that they can kill a mammoth with one blow. Ridiculous? No. Evolution always takes a different path. Right now, we are reaching the point in the development of the universe where what was created by the previous arm of history can be utilized by the new arm without integrating old structures into the new. Only the accumulated information will be used, meaning that in the scenarios we have described, only the accumulated knowledge will travel through space and will no longer need those who sent it, just as we do not need supernova stars that provided us with chemical elements. Planetary civilization may perish, but information from it will be transmitted by other flaring and gaseous powers, points of intelligent planets. Information soars through the universe like a cloud or a network, much like language or culture, nurtured by born and dying humans. Language changes over time, and the universal information network will evolve, accumulating internal complexities. But will this comfort us?